లే ఊరు పిల్ల
వచ్చినా మళ్ళీ నేను అడిగిన
Good morning, Senthil.
Hi, good morning, Satya.
Senthil, one more doubt on the assignment. This is related to the calculating the value of kappa.
Okay, kappa statistics.
It's not yet covered, right?
Yes. We will cover that. So kappa statistics is a kind of statistical evidence that your model is really predicting this stuff. No problem, we will be covering that.
Okay. I tried it myself, but there is nothing called threshold in it. So maybe.
Sure, we will cover that.
Okay.
Yeah.
Thanks.
Hi sir, one doubt in the assignment.
Hello.
Hello.
Yeah, please.
Yeah, sir. In one question, they are saying data set that are involved in multicollinearity. That means we have to select features which are more than 15 or less than 15.
So free of multicollinearity means less than 15. Actually, less than, ideally speaking, less than 5. But anyway, less than 12 with respect to VIF is fine.
Yeah,
So
no, actually the question states like identify the features from the dataset that are involved in multicollinearity. So what does that mean? Like
uh,
those are like less than 15 or more than 15?
that is both the thing you can project now. So we can't tell very say if you are constructing a logistic regression model, the only assumption that you need to look for is data should be free of multicollinearity. So out
Mhm.
of the n features that you have, how many features are responsible for multicollinearity that you have to identify and you have to remove that.
But
Once you have the two,
y- yes, sir, I got that. But the second part is after that split the updated data means we have to remove those multicollinearity and then we have to split that, right?
of course.
Okay, the
So
wording I got confused, which are involved in multicollinearity. So
yeah, which is involved, which is responsible for multicollinearity, something like that. They have framed the statement.
okay, okay, sir. Thank you.
But the trick is there is nothing which is more than 15 VIF.
Oh,
No, we did happen to have.
No, I mean after post scaling, if we see we don't have. So
Okay, I think yeah, I didn't scale. Maybe that's the reason.
yeah, if you do that partial scaling, most of the time that multicollinearity effect will reduce.
right.
Okay, okay. Yeah, thanks.
Yeah.
Good morning, students. I hope all of you are able to solve the in class because we'll be meeting like in this session. So in the next in class, we'll be releasing naive bias and KNN on that with the quiz part.
In class assignments, right, ma'am?
Yeah, in class
Yeah,
assignment.
yeah, ma'am. Yeah.
No problem, no, for solving. The decision tree and the logistic was given for this week. And next week will be KNN and naive bias. I'll also upload the solutions by tomorrow because the deadline ends today. And so tomorrow I'll upload the solutions. Please go back and check your values. If there is a greater range, we can see whether what is the error and where we have done our mistakes and we can correct it later. Good morning, Dr. Senthil.
Hey, good morning, Lena. Shall we start, Lena?
Yes, sir. Yes, sir. We can start. Yeah.
Yeah. Hello, very good morning to all. So as I told yesterday, today discussion will be on neighbors and k nearest neighbor algorithm. So these are the two algorithms that we are going to decode in our today's session. So first we will be discussing neighbors, then I'm moving into k nearest neighbor. So both these algorithms are kind of simple algorithm in terms of the math involved in it, right? So very straightforward, simple mathematics only we are going to use to do our classification task. So out of these two algorithms, your Naive is going to use the Bayes theorem as a basic equation. So fundamentally in Naive, we are going to compute something called conditional probability. But the only thing that you need to understand is how that conditional probability concept has been taken towards classification result or classification problem. So that map is actually is essential to understand the Naive algorithm. So you know that Bayes formula, which is very simple and straightforward. But the only thing, as I told, is how that posterior probability, prior probability, likelihood, probability of input, everything, how we need to relate to the classification problem. So that in that sense, we are going to study Naive with a couple of examples how to decode the Naive equation towards the classification problem. And also there are different variants of Naive. We are going to discuss about those different variants of Naive algorithms. And finally, we are going to do some kind of Python workout on how to implement all those algorithms. So as for Python workout, I'm plan to do in a two-way. One is without using any function from the sklearn, we will be just implementing the Naive based upon its base equation. Followed by we are going to implement the same Naive with respect to the three different variants or three different functions available in sklearn. So this is what we are going to discuss in the first half of the session. And in the second half of the session, we are going to discuss about the mathematical part of k-nearest neighbor algorithm and also implementation part in Python. So that is what the agenda for today's session. So as some of you requested, while I am doing KNN, I will be using some multi-class data set. That is, as of now, the data set that we are using is having only 2 class in the output. So while I'm doing the KNN, I will be using some multi-class data set. So the output column will have more than 2 levels. So what are the kind of, how to understand the different metrics, how to understand the confusion matrix, how to plot the ROC curve with respect to the multi-class, that we will be discussing. At the end, quickly, I will also go take you through how to balance the data set. Right. So directly, I will take you to some code after explaining the concept of imbalance. So these 3 topics I planned for today's session. So let me share my screen. Just a minute. I can't. Fine. So people already discussed this Bayes theorem. So this Bayes theorem is basically a probability technique through which we can compute the conditional probability. So using the Bayes theorem, I can find what is the probability of P or what is the probability of B. Say what is the probability of event B with the condition the event A occurred. What is the probability of event B with the condition that probability with the condition that the event A occurred. So now how to expand this? Can anyone help me? If I want to find the conditional probability P of B over A,
is the likelihood of
P of A given B,
P of given B, and then
P of A given B
into P of A,
P of A, P of A,
by
P of B,
P of B,
P of A or P of B. The probability of P of B divided by your P of
P of A.
A.
P of A.
Right? So this actually gives you the conditional probability. So Bayes' theorem has been defined through this equation. So through which we can compute the probability of B for a given A by using its likelihood. This part its likelihood. This part is prior probability. And this one we can call it as posterior probability. These are some kind of statistical term. And this is nothing but evidence. Right. So now our discussion is more on how to interpret, how to take this equation towards the classification model. So you have done a lot of problems, worked out, and all those things with respect to this Bayes' theorem. I'm going to be focused on how to take this equation towards the classification problem. Say, provided, say in classification problem, we have some kind of structured data set. Structured data set means we have 10 column of data and one 10 column of input data and one column of output data. Right. So now how can I apply my structured data which is having multiple input column and one target column on this equation, and how can I make the classification results using this Bayes equation? That is what our objective. That is what we are going to discuss in our today's session. So say while you are having an equation like this where B is one event and A is one event, I'm just going to slightly change this equation with the kind of terminologies that we are used generally for our classification model. Generally, that output we will be representing with Y and the input we will be representing with X. So slightly I am modifying this equation like P of Y given X. So what it means, I'm just finding out the probability of the output. While I'm saying the probability of the output, in classification column, there is one output column, say example, whether the patient is having cancer or not. So that is nothing but your output column. So how many classes or how many levels will be there in the output column? How many levels will be there in this output column? Two levels. So I can even slightly modify this equation like probability of Y is equal to C1 given X. Probability of Y which is equal to C1. So what is the probability that the output column to contain class 1? Right. So what is the probability of cancer? Say the output column is having only 2 level cancer and non-cancer. I'm just going to find what is the probability of cancer for a given input. What is the probability of cancer for a given input? Because that input has been occurred, input has been given to me. Now my task is to compute with this given input, what is the chance that that particular patient is having cancer. So that is the reason why we are going to use this Bayes formula, this condition probability formula, because input is given to me. With respect to this input, I have to make the decision about the cancerous nature of that particular patient. So for the given input, what is the probability that he will have cancer? So in order to compute that towards the classification result, I'm just making use of the Bayes theorem. So this equation I'm slightly modifying as probability of Y is equal to C1 for a given X. So now this side of the equation. So hereafter I'm just writing Y as YC1, or simply I can even write like this YC1. YC1 means class 1 in the output column for a given X, which is equal to probability of X given YC1 into probability of YC1, the whole divided by probability of X. right? So this is the probability of cancer. What is the probability of the person to have cancer for a given input? That is what I want to compute. For that, I'm just computing one likelihood. What this likelihood is telling, say, among the cancerous group observation, this YC1 is say cancerous group observation. Among the cancerous group observations, what is the probability that that particular person can have one such an input pattern? Say, for example, X is equal to smoking habit. Say X is one feature, and that one input feature is smoking habit. Then smoking habit is going to have two levels, yes or no. Then this P of X given YC1 is nothing but among the cancerous group, because YC1 is given. So these are the cancerous patient which is given to me. So among the cancerous patient, what is the chance that an observation to be a smoker? That is what given by this likelihood. Because this is a classification problem, it's a supervised learning, so I have data already in my hand. So using the data among the cancerous group, what is the chance that this particular observation could be a smoker? Because this X talks about the input feature, which is nothing but the smoking habit. So that actually I'm computing separately, that we are calling as a likelihood. Then this part P of YC1 you can easily calculate, right? So for a given classification data, can you calculate this P of YC1? What is P of YC1?
The class.
All the cancerous patients.
Target business.
Divided by total number of value.
Exactly. So how many people are having cancer divided by total number of observation in this data set. So it's a straight probability of class 1. So that actually we are calling as a prior probability. And again here it is P of X. P of X is your input. Say here your input is only one column, which is nothing but a smoking habit. Then what is the probability that smoking habit to be yes? So that is nothing but your P of X. So once I have computed these three numbers for a given input, if I substitute in this equation, I will get the probability for this given input. What is the probability? Say if X is equal to smoker equal to X, yes, that input is one input is coming to my model, and I have only one input feature. That input feature is a smoking habit. That smoking habit is equal to yes. Then by using my past data, what is this likelihood? What is this prior probability? What is this probability of that input? Everything I will calculate, and if I put it in this equation, I will get like what is the probability that a person with smoking habit to have cancer. That has been given by this equation. Now, along with this equation, I also need to find the same equation. Once again, I have to find with respect to the class 2 also. What is the probability of that given input? Say the given input is smoking habit equal to yes. So what is the probability for a person with a smoking habit to belongs to the class 2? That is also I need to find, right? Class 2 is say benign, that is no cancer. So what is the probability for a given input such that that particular observation belongs to class 2? That is also I need to compute. For that, I'm going to use the same equation. The only thing is P of X given YC2 into P of YC2, the whole divided by P of X. So now I have two probability for one given input. So there is one input for which I have to make the decision about its class. So I'm just applying that one particular input pattern in both those equations, and I'm getting two probability. One probability towards the class 1 and one probability for class 2. So among these two probability, if P of YC1 over X is high, then I will be telling that this particular person is having cancer. And if the probability of P of YC2 given X is more than P of YC1 given X, then I will be making the decision like that input feature or that input the input observation belongs to the non-cancerous class. So this is how we have to use this Bayes theorem to make the classification decision. So it's like very simple and straightforward because I'm just using only one input feature. That X is actually simply one input feature. Even for multi-class, it will work perfectly. Even for a multi-class, you have to find P of YC1, P of YC2, P of YC3, P of YC4 like that. For each and every class, you have to find the probability. Then you have to compare all those probability, whichever the probability is high. If we see YC3 is high, then that particular input observation is belongs to class 3. So that decision is simple and straightforward. Multi-class, you can easily apply this towards the multi-class. But the problem is, what if my X is having multiple columns? What if my X is having multiple columns? What if my X is having some column which is continuous numeric in nature? So in that sense, we have to decode the Naive-Bayes algorithm. Let me write one another equation. Yeah. Say, I have 3 input features. Like one is the same one we can take. Smoking habit. Say smoking habit, I'm just mentioning as SH. And age and drinking habit. Drinking habit in my equation, I'm just going to write it as DH. Using these 3 input column, I'm going to predict the cancer. All right. So cancer is having 2 levels. C1 is say malignant, and C2 say benign. Right. So this is my structure of the data set. I have 3 input columns which talks about the smoking habit of an input person, age of the person, and drinking habit of that person. And the output column is having 2 levels in it. One is for malignant, one is to represent the benign nature of the cancerous tumor. Right. So now this is my data set. So now, how can I apply the same Bayes rule or Bayes theorem on this equation? So now we know that we need to find probability of malignant, right? I'm just writing this as M. Whenever benign, I'm just using this terminology B. So what is the probability for an input to be a malignant given what? Given smoking habit. Yeah, I'm just writing like given SH, age, and DH. Right. So what is the probability that input data to be malignant for a given SH, for a given age, for a given DH? So SH could be yes, age could be 44, and DH also could be yes. Right, or any value for SH, age, or DH. For any given value for those 3 parameters SH, age, and DH, what is the chance that that particular person to have cancer, to have malignant tumor? So that is what we are going to compute. Can anyone tell how can I write the other part of this equation? How can I write the other part of the equation? How can I write the likelihood for this?
Probability of SH given M, again into probability of A's given M, and probability of DS given M.
Yeah, but whether statistically that is correct, the probability rules are actually allowing it. Actually, here we are actually making the decision about one class using the multiple parameter. Then obviously we have to apply something called chain rule. Yes or no? So statistically, in probability world, people will apply something called chain rule. So let me first write with respect to the chain rule. So probability of smoking habit given all other things, age, comma, DH, comma, malignant, then into probability of age given the remaining thing, DH, drinking habit, comma, M, into probability of DH given M. So this is actually a chain rule. So if you want to compute the correct likelihood, this is the way that you need to decode it, right? So probability of smoking habit given age, DH and M into probability of age for a given DH and M, and probability of DH for a given M. So this popularly known as chain rule. So whenever you have compute a conditional probability with respect to multiple input, this is the way you have to expand your equation. Into this is, say now this is your whole likelihood into P of M, right? Into probability of M, the whole divided by probability of that input. So again, the probability of here also we have to expand it, but anyway, because we are going to find this for probability of M, and also we are going to find for probability of B. We are going to find what is the probability of malignant for a given input, and also what is the probability that observation to be benign for a given input. For both the things, we are going to write this equation. So in both the equation, the denominator is same, no? P of X, P of X. So obviously, because the input, while I'm checking the probability for malignant and probability for benign, this input is same. For the same input only, what is the chance that it becomes to be malignant or to become benign? I'm just going to find through this equation. So I don't much worry about this denominator, because both the equation denominator going to be remain same. So while I'm comparing the effect, only the numerator effect I can compare. I no need to actually expand the denominator part. So I'm just now I'm just keeping this P of X, right? But this probabilities are very difficult to compute. These probabilities are very difficult to compute, and it is computationally heavy. It is computationally heavy to compute those numbers, especially if you have more number of features in your data. Then obviously it is actually computationally heavy to compute these numbers, right? So it's mathematically heavy to compute these numbers. So naive Bayes is actually assuming that while doing its calculation, naive Bayes is assuming that the inputs are independent, right? So naive Bayes is assuming this condition, like the inputs are independent. But the kind of thing is, say it is not like we are going to check whether these are all independent. So generally, what is how will you check to comment about this assumption? What you will do to understand whether the inputs are independent or not? Multicollinearity, right? Basically, we have to find the correlation, or multicollinearity we have to compute to comment about the independent. And also, if it is not, some column of data is actually depend upon the other group of data or other column of data, then we will be computing something called VAF, and based upon VAF, we used to drop the features. But here in naive Bayes, we are not actually going to perform those kind of things. So we are going to assume that all the input features are independent of each other. And surprisingly, this mathematics, it's giving us the answer almost correctly even if it is not actually independent. Even if it is not actually independent. So even though there is a dependency, this actually almost predicting in the same way. There is no much of change. But we are actually assuming this condition just to simplify this equation. If I assume this condition, if I consider this condition like the inputs are independent, then this equation for the base that I have written can be written as one of our participants told, like I can simply written like P of SH given age, sorry, P of SH given M into P of age given M into P of DH given M into P of M, the whole divided by P of X. So now I have simplified. I have just removed this chain rule and I have just written that the conditional likelihood with respect to each and every input separately. This has been allowed. This way of writing the equation has been allowed only if you consider that the inputs are independent. Only if the inputs are independent, you can write your expression of the naive like this, or expression of the likelihood like this. But it has been proven like even though it is not independent, the results between these two things are not actually drastically changing, because the same kind of analogy only we are using for the other class also. For while we are computing the same probability for benign, the same kind of assumption that we are making, and we are actually decomposing this chain rule in the same way, right? By considering that all the inputs are independent. So performance wise, surprisingly, it is actually producing the same result or far result, even though your inputs are not actually independent, right? So this kind of equation you can write only if the inputs are independent. But even though in some cases, even though in your data there is a correlation, the data are not independent, but still if you assume like these are all independent, and if you decompose your chain rule like this, the results are not drastically changing. Your model is have the ability to predict the output in the same way as this equation. So that is the reason why this base here is actually known as naive base. Why the base here is known as naive base? Exactly for this reason. Naive base is actually assuming like all the inputs are independent, but we are not actually doing anything to make the data independent as we do it in some other model like linear regression or logistic regression. In order to make data to independent, we will be applying some multicollinearity test or multicollinearity analysis, and we will be dropping some of the feature which is not actually depend on each other. But here we are not doing any such a kind of thing. The only thing is we are assuming that simply that data are independent of each other. So that assumption allow us to write this complex equation in a simplistic way. But this equation is still valid, or this equation is still producing the far good performance, even though there is some relation between the input variables. So that is the reason why it is known as naive base. So in a naive way, it is actually producing kind of same output, even though this assumption is violated, even though if this assumption is not really exist in your data. So this equation that you have framed with respect to this assumption is actually doing well for correlated data also, correlated input also. So that is the exact reason why this base equation is actually known as naive base. Right? Understood? Any doubt on this?
I have a doubt. So, so we have assumed that the input features are independent of each other, right? So, mathematically, when we try to compute, so do we check the multicollinearity between these features and then determine whether the features are independent? Is it so, or like
No,
I'm just
if that is what exactly I told. Like say we are not say we are actually simplifying this equation from this form to this form, from this form to this form, by simply assuming that the inputs are independent, but we are not really going to bother about that dependency. Even if it is if there is a dependency, we are going to use the same independent condition equation only. That is the exact reason why this base is actually known as naive base.
Okay, okay. But when do we know actually, like when we should apply naive Bayes in that case? Because yeah, we understand that we are just assuming it, but in what scenario do we actually apply this algorithm?
No, see, the thing is, this is say naive Bayes. It's a kind of base model always. So naive Bayes is a kind of algorithm people will use as a first algorithm for any huge data, right? Just to understand the predictive ability, whether there is any predictive ability exist in the model or not. That direction that we will get, whether using this input, whether we can predict the output or not. Because if you see all the elements here, like what is the likelihood, what is the prior probability, using that only we are actually mapping the input output relationship. So in that sense, naive Bayes is a kind of base model that you can apply on any given big data set. Even if you have a very huge data set, just imagine finding these three probabilities is not a kind of big task, right? So you have to just filter the data and you have to find those probability for each and every class with respect to the corresponding group. So mathematically, this logics are very simple. So in that sense, well, for any given data set, as a first model, people will build the naive Bayes model that will give some kind of understanding. Okay, with naive Bayes itself, I can able to predict this much. So on top of it, then people will think of some kind of nonlinear model and they will build so on. So most of the time, apart from some kind of text analytics, nowhere you can find the naive Bayes as a kind of final model. So it is actually a kind of first level of machine learning model through which you can understand whether for a given input, really I can able to predict something about the output. So that initial understanding you will be getting. So always naive Bayes results are kind of poor compared to even your logistic regression, decision tree, random forest, and so on. Right?
Okay.
So this is, say, as I told, this is a simple probability concept. We are actually just extending towards the prediction. So mathematically, this is very simple. Say if client want you to just show some kind of first level result as quickly, so just take the data. Even you no need to just do the feature engineering and other thing, because automatically if that particular feature is not contributing towards that class, that corresponding likelihood will really become very low. All those things it will happen, and just like that, with respect to those probability value, you can give some kind of output numbers for your model. Of course, that output number is not actually really good, but still, say if you are getting 60%, 70% with your naive Bayes, then there is some kind of pattern. There is some kind of, just only using the probability, you can capture the input output relationship by 60%, 70%. Definitely, there is a scope for this data set to improve its performance through some other nonlinear model. So typically for that kind of purpose, people will use this. And also using naive Bayes, you can't really explain your model coefficient or a model interpretation. All those things also you can't really do it. It is just to do the prediction, and also you can't use this naive Bayes for regression. You can use this naive Bayes only for the classification problem. So it is not a very powerful model, but at the same time, this could be a very first level of model through which you can understand the input output relationship. So you no need to actually do any kind of multicollinearity treatment. So it has without by keeping all those features as it is, but simply assuming that this is all those features are independent between each other. We are actually simplifying this equation to this form, and there is no kind of great difference between these two form of equation in order to predict the correct class for the given input. So that is the reason, even though if the data is not not completely independent of each other, the columns are not independent of each other, we are assuming that it is independent of each other. That is the reason why it is known as naive Bayes. Right?
Yes, I got it.
Yeah. Now similarly, you have to find the same equation for again P of benign with SH, H, DH, and the same equation P of SH provided it's benign, P of H provided it is benign, P of DH provided it is benign, and P of benign the whole divided by P of X. The whole divided by P of X. So this is the exact reason why I told that no need to actually expand this, because here also the same input, here also the same input. For the same input, what is the probability that it belongs to malignant and what is the probability that it belongs to benign? Both are things that we are computing. So while I'm calculating this, I'm just getting this as 0.65, and when I'm calculating this, if I get this as 0.35, then obviously this particular for the particular input, the class that I'm going to allot is malignant, because that malignant probability of malignant for a given X is actually more than the probability of benign for a given X. So obviously the class that I'm going to allot for this particular input is malignant. So likewise, your naive Bayes will actually works. Now,
sir, one question.
Yes.
How this algorithm works for continuous variable? Age is continuous, right?
Yes. That is what exactly I'm going to address now. How to compute this part, how to compute this part, and how to compute this part.
Sure.
Let me explain that. All right. So now we have framed the equation. Fine. As one of our participants asked, some here probability of age for a given malignant group is something like, I'm just going to find the probability for continuous value. And these two things are going to have yes or no level. This is a smoking habit and this is an drinking habit. So there is no issue in computing this, right? How we can compute this before going into age? Can you tell me how will you compute this? Likelihood.
So how many person is smoking divided by total number of people?
In malignant group.
P of M by S.
Total number of malignant.
Yes. So it is like, I'm just writing here. Filter out. Because we have the data. We have data. We are not actually approximating or estimating anything. Right? Filter out data with only M class. Given M. It is given M. So you have to find the probability of SH, probability of smoking habit, only for the malignant group. Yes or no? Yes or no?
Yes.
Yes, sir.
So filter out the data with only malignant class. Then in this malignant class, how many smokers are there? How many smokers are there? So say provided that you need to find the SH which is equal to yes. SH equal to yes if you want to compute. Then filter out the data with only M class. And in that, totally how many number of smokers are there? So say if you have, say the malignant class are actually 50. And out of the 10 or 20 are smokers, then this probability is equal to 20 divided by 50. This is as easy as this. So just filtering out the data for one particular class and counting the level in that class will give you the probability of smoking habit to be yes and probability of smoking habit to be no. Right. So computing this is simple and straightforward.
The intersection of SH and M by probability of M.
Sorry?
The probability of SH intersection M by probability of M.
Yeah, of course. That is using those equation and other things. Now we have a data anyway in our hand. So we have, this is a supervised learning. We have a data in our hand. So while we are computing that intersection and all those things is it's is this step only the kind of 2 steps that I have written. Take only the malignant data, and from this see how many data are belongs to smokers. So that is the probability that SH to be S for a given M.
Sir,
So
by default it consider 1, right?
Sorry?
By default it consider 1.
No,
Yes.
it depends upon for which input. Say this we are computing in order to compute this, right? This is our primary objective, right? So what is the input that you have now in your hand? For which patient you have to compute this? Say the input patient information is SH equal to X, age equal to 35, and DH equal to no. He is having the smoking habit, and his age is 35. He don't have drinking habit. For him, you need to find what is the probability. Then in that case, you have to find this SH with the for SH equal to S, and you have to find the probability of age for 35, and you have to find the probability of DH for no.
Same can be for no also, no? SH equal to no.
No, why? Because I want to find this for this input. What is that overall probability that I need to find?
Okay.
This is one input which is comes to me. For this particular input, what is the probability that he is having cancer that I want to find? So in this equation, I have to compute. Say if SH equal to S, what is this probability? And if age is equal to 35, what is this probability? And if DH equal to no, what is the probability? Then if I compute all those things, I put it in this equation, then I will be getting the P of M for a given input. Right? So whatever the input that you are having in your hand, for that level, you have to compute this. So similarly, you can also compute for DH of M. So for any level in DH of M, you can compute the probability value. Now, how can I compute this for age? How can I compute this likelihood for age for a given M?
Sir,
Yeah.
just to reiterate, okay, first, both benignant and malignant both are there, out of which to find M, caused because of SH, that is smoking, and caused because of age. That is how we do, right, sir?
Yes. Hello? Hello? Am I audible?
Yes, sir, you're audible.
Yes, sir.
Yeah, I missed your question. Can you repeat?
Yes, sir. First, out of which we have both M and B, 2 classes. In that, through smoking, how many malignant are caused? That is how we are finding, no, sir?
Yes, that is P of SH given M. Likelihood of a smoking habit for a given malignant class. You got the point? Or are having confusion?
Okay, sir.
Right? So we can find this probability of SH for a given M and probability of DH for a given M very easily. How can you find the probability of age for a given M?
Yeah. Can we take threshold for age, like any condition?
You might
based
say
on that.
If there is any continuous probability, if you want to find, then what kind of approach that you will generally use?
We use range.
Take some interval,
Range
interval for age.
Intervals.
Yeah, but that ideal thing is for age you can compute your mean and standard deviation, right? Because age you have for all the observations in the malignant class, you have age and you have age. So with respect to that age, you can find the mean and standard deviation. With that mean and standard deviation, you can plot the distribution, right? Using that Gaussian distribution. Yes or no?
Yes.
Right. So once you have this distribution with you for an mean value of age and the standard deviation of that age, Now say this age is equal to 40. Then this axis is actually in terms of age, right? So here say this is the 40. Then for 40, what is the y-axis? If you see, that is nothing but the probability value of age to be 40 among the malignant group, right? Yes or no?
What is y?
What
Probability.
is the y in distribution? This is a cumulative, it is your distribution graph, right?
Yeah, probability, yes. Yeah.
Right, so it's a probability. So what does that distribution graph will tell? So what is the frequency of occurrence of each and every level in your input? If it is continuous probability distribution, you can find it for any intermediate number between any minimum value to maximum value. So once I plotted this distribution curve for the age column, because all the past data of age I have for the malignant group. So using that mean and standard deviation, I can use this graph. What is the equation for this graph? What is that equation? Can anyone tell?
X minus mu divided by sigma.
No.
But if you're talking about normal distribution, then 1 divided by 2 pi.
Yeah. So we have to 1 divided by root of 2 pi sigma square
e to the power
variance
of
x minus
xi minus x bar
divided by sigma
square divided by 2 sigma square, right? And also the whole square, something like this. So using this equation only, actually we are fitting this age data, past age data, and we are coming up with this distribution. And for any given new test input, if we fit that new input in this curve, the corresponding probability we can get. So this is how your Navier will calculate the probability value for the continuous data.
Sir, but as per the property of normal distribution, we can't calculate point probability, right? Age equal to 40 is point probability. It's not range probability.
Yeah, but but this Gaussian distribution variant of Navier is actually using this distribution function only to fit and to compute. So this is in a cumulative distribution function only you can't compute, right? So here that logic will remain same, no? Say how the say if you have an age column and if you are plotting it, then obviously for each and every value of age, for each and every value of age, what is the probability? With respect to that only we are plotting this graph, right? So what is wrong actually in once again retrieving the same probability value from that graph? So that is the kind of idea it is actually using. I don't know whether really any such a kind that about the statistical rules, but I'm damn sure that that Gaussian Navier is actually working in the same way only. So it is actually using this distribution function and it is plotting it. And for any given input, it is actually applying that number on this function and it is taking the corresponding probability value and it use that probability value as a likelihood in our base equation.
And this is assumption, right? Gaussian assumption. Again, we are assuming
assumption. Say if it is not for a Navier, I told like in Navier there are 3 variants, right? This is the Gaussian variant of Navier's algorithm. So for which that is an assumption like your data should be normally distributed. So generally, if there is more of outlier, then we have to treat the outlier. I told no. So some of the algorithms are sensitive to outlier. So we have discussed linear regression, which is sensitive to the outlier. So this is the second algorithm which is sensitive to the outlier. So whenever you are using the Navier, you have to make sure that your data is free of outlier. Because if outlier is there, then normality will be get affected. Then this equation that we are plotting for this continuous numeric variable doesn't have more logic in it if it is not normally distributed, because the kind of equation we are using to fit those numbers is normal distribution equation. If your data is not normally distributed, then obviously there is no point in fitting this number and finding the probability. So while if you are using the Gaussian Navier, then definitely you have to make sure that your data is normally distributed. If not, you have to perform some kind of transformation to make sure that it is close to normally distributed.
Right? Is there any other way, sir, to find probability of?
Yeah, binning kind of stuff. You can
Yeah,
bin,
binning, like interval.
But I'm explaining with respect to what that sklearn naive is doing. So sklearn naive externally, if you are writing, we can do such a kind of thing. We can bin it, and we can for that group continuous number, we can bin it. For the each and every bin, we can find the probability, and that we can use as a likelihood in our equation. But naive is actually doing this kind of approach only in sklearn. Right? Got the point?
Yes, sir.
Yeah. So likewise, it can compute the probability for the categorical variable easily, and for the numerical variable, it is using the distribution concept to find the probability. So once it has all those probability, we have to substitute this in both the equation. So in this equation also I have to substitute. In this equation also I have to substitute. So for this equation, I have to find this likelihoods with respect to only the benign group. For this equation, I have to split my data, or I have to filter my data with respect to only malignant group. And among the malignant group, what is the probability of SH, what is the probability of EH, and what is the probability of DH I have to compute. And here for this equation, I have to filter my data with respect to only benign group. And among the benign group, what is the probability of SH, what is the probability of EH, and what is the probability of DH I have to compute. And once I substitute all those numbers in these two equations, we will be getting these two probability. Which are the probability is high, I have to allot that input in that particular class. So that is how we are going to, that is how the naive algorithm is actually making the classification decisions. So with this,
so here for the age, we will calculate one by one for every value, is it?
No. So that is say you don't need to calculate for all the ages. So say you whatever the age for which you need to make a decision, for that age alone you just
That alone
calculate.
we will calculate. Okay, so we cannot make a model out of it, or like a threshold.
Sorry,
like there is no such concept for threshold on this continuous variable, right? We have to calculate one by one based
yes.
on the
Based upon the input data. So whatever the test data, which is coming to us, for that test data, in that test data, in first observation, age is 42, means for 42 I have to compute. For the test observation, the second value is 33, means for 33 I have to compute. So like that, I have to compute for each and every test observation. And for each and every test observation, I have to find all those three probabilities: P of SH, P of DH, and P of EH. And then I have to apply in this equation, and I have to make the decision about that particular observation, whether it belongs to malignant class or benign class.
Okay, thanks.
Yeah.
Sir, so one question. So I did not get the last part. So for each value in test data, I mean, I did not get that part.
See, I have a big data. Say, I have totally 1000 observation into 3 columns for the input, and 1000 observation for, and 1 column for output. So what is this 3 columns? The 3 columns are SH, EH, and DH. Right? This 1 column is cancer or not, or malignant or benign, MRB, malignant or benign. So now with this whole data, you can find this prior, what is the probability of M, what is the probability of B, all those things you can compute. So now, for example, say one P is coming, say one new test data. One new test data is coming. For this, your smoking habit is yes. Your age is 42, and DH is no. And also there is in your test data, you have say 2 data, no, 30, no, right? So now for this 2 data, you have to make the class. You have to tell whether it is benign or not. You have to make a decision here and here. How can you make this decision? How can you make this decision?
We can multiply the probability of SH, age, and DH.
Probability of Yeah, that is, say SH equal to S. So I am just going to frame this equation. Probability, I have to find this probability of malignant given SH equal to S, age equal to 42, DH equal to no. This is what I need to compute it, right? Yes or no?
Yes.
Yes.
For
Right.
each row we need to compute, right?
Yeah, for this each row you have to compute with respect to the test data, for which data you want to find the output. For that you have to compute. Now for this, how can I compute P of SH equal to S given M into P of age equal to 42 given M into P of DH equal to no given M into P of M, the whole divided by P of X. Now how can you compute this P of S for a given M? So with respect to this whole data, you have to compute what is the SH, what is the P of SH equal to S for a given M, and how can you compute this P of age of 42 for a given M with respect to this whole data? That is, whole data means with respect to this whole data, you have to filter out only the malignant group. For that malignant group alone, how many persons with smoking habit S is there, that probability. Similarly, you have to plot the distribution curve for that age of the malignant group. With that distribution graph, you have to find what is the probability for age equal to 42. Then similarly, you have to group this data with for the malignant group with the drinking habit equal to no. Then among that, for that you have to find the probability. Then this probability of M is for the whole data, 1000 rows of data, how many people are actually having the malignant. So if you multiply all those things, that actually gives you the probability for this. Similarly, you have to do this once again. You have to construct this equation with respect to the second test observation to make the comment about its class.
And we should be doing it for benign as well, right? For the first row.
Yes, of course. This we are not going to do only for a malignant. This we have to do for the first row itself. We have to do this for benign also. Then what is the probability of malignant and what is the probability of benign? We are going to see among these two which probability is high. Then we are assigning this particular observation to that probability.
And what is P of X? What is X here? X is a sample, but
no, again, this is a kind of chain rule we need to apply. P of X equal to SH equal to S, P of age equal to 42, P of DH equal to no. That I have to find here. But the only thing is, whether for finding malignant or while finding the benign, for both the things the denominator is P of X only, no?
Right.
So that is the reason why we are not actually computing it, because that thing we can that effect is going to be there in denominator in the same way for both benign and malignant. So just I'm going to see this value, whichever the value is high, I'm going to allot that particular sample to that corresponding class.
Okay.
Sir, if there is a new label in the data, then the probability will be 0, right? It will always go to another class.
New label?
Yeah.
Yeah, obviously you can't say. It is not possible, right? Say if in your so you are asking like in 1000, in this 1000 data there is only 2 label, but here one new label which is coming, which is not there in this 1000 data. That is what your question, right?
Yes, I mean independent features I'm talking. So let's suppose in SH, let's suppose not given label has come to test data, then the probability will always go to B, right? Benign.
Yeah, definitely. Say any machine learning model actually fail in that case. So that train scenario, whatever the levels which is there in one particular column, with respect to your train data, that only should be there in the test data also. If in test data some new levels comes, then obviously everything will go wrong, right? So even if you do some kind of dummy encoding, so there is one column for each and every level. So suddenly one new level coming in the test data, in the sense machine learning model don't know how to use the data, for which column it need to make 1 and which column it need to make 0, right? So that kind of scenario you can't handle. So you have to make sure that you are testing your model for that same levels that you have in each and every column of your data, column of your trained data.
Yeah, even age also. So let's suppose the training data has age between 18 to 50 and test data got 55, then the probability will be 0 in that case, right?
Yes, obviously.
Okay. Because one probability will be 0, then because it's a multiplication, the entire probability will go 0.
Yes.
Okay.
I think in that case, sir, SQL take care of by using a smoothing, right? It's adding one value in top and the bottom.
No, that is count. I will come to it. That Laplacian smoothing, that is fine. That is word count and other things also. Generally, what he is telling is like say in general machine learning problem, if one level is not at all there, that is the advantage of one particular variant. We are calling that as a multinomial Navier. So that actually have that special characteristics of Laplacian smoothing. That is not common for all the machine learning algorithm, right? So generally, machine learning algorithm don't have the ability to handle something new directly in the test level. So whatever for which you have trained, that only you have to give it during your test level also. Suddenly, if some new level, some new feature is coming in the test level, definitely your machine learning model don't have that ability. That Laplacian smoothing I will be addressing. That is with respect to the externalities concept, how to incorporate that. There is some kind of extra provision is given in the Navier to handle it. But obviously, say your data is about only for the age of 18 to 50, and suddenly there is some age is coming as 60, then obviously your model will won't handle it. So that kind of issue will be always there.
I have a question. So here, when Satya was mentioning, like we have to calculate for benign as well, right? So after calculating for benign as well, so do we need to sum up these two probabilities and the whatever the final probability we'll get, and that is the answer, is it, for the
highest?
first row?
No.
The
Is
highest.
it? Okay.
The highest of it.
No, that is between. See, you are calculating two probability. One is probability for malignant and one is probability for benign. Out of these two, which probability is high, you have to allot your test sample to that particular class. If I have written here no, so say here this probability I am getting as 0.65, and here this probability I am getting as 0.35. Then this data I will be allotting for that malignant class, because the malignant probability is 0.65, whereas benign probability is 0.35. So I'm just saying that this particular person is having cancer.
Sir, can we not take 1 minus?
Got it. Okay.
So say that is this benign value. Say you are telling that that benign value is always 1 minus of your. Yeah,
Yes,
that's true.
is always.
Yeah, that's true. Provided that you are actually calculating this P of X denominator, P of X in the denominator. But computation of P of X we are actually avoiding, no? So as we are avoiding the P of X computation, even though this is a kind of probability equation, we won't get exactly in terms of probability. Only if you compute P of X and if you divide that, then you will be getting in terms of probability. Otherwise, we won't get the probability value directly. We'll be getting some number. Whichever number is high, we are going to allot that particular class for that particular observation, right? So just move on. Value without P of X, how we are what is the value that we are going to get? All those things I'm just going to show you in a Jupyter notebook. We are going to execute this equation as it is, because sometimes students will have the confusion over understanding this equation, how this is happening, how to calculate all those things. That is the reason why exactly I will do this implementation. Whatever the equation that I have discussed with you now, I'm going to implement this in terms of equation itself in our Jupyter notebook for an real-time data, right? Without using the any function. First, we will be going to implement this as it is, so that you can easily understand it. So better we can go to it, and again we can come back to the board to discuss about the some text analytics example with respect to the Navier. Because we just discussed all those equations, I feel like straight away I will implement that. Everyone having this breast cancer data set with you, right? That cancer data. So everyone having cancer data with you?
So I think yesterday it was shared.
Sorry?
The one shared yesterday, right?
Yes, yes, yes. Answer data I don't have. Fine. So this is the data which is having totally 33 columns, right? Like so many shape and texture measures, like what is radius, what is texture mean, what is perimeter mean, area mean. All those measures has been calculated for the tumor, right? So there is a tumor that they have segmented from the mammogram images. So from that images, they have actually calculated those numbers by doing some kind of image processing, by applying some kind of image processing techniques. What is the radius of the tumor? What is the perimeter of the tumor? What is the area of the tumor? What is the smoothness of the tumor? What is the compactness of the tumor? Like that, all those measures that they have calculated. And ID talks about each person's unique thing, and the diagnosis talks about the nature of that particular tumor, whether it is malignant or benign. And here there is one unwanted column is there, unnamed 32. So we have to remove that. So this is a data set for which I'm just going to apply Naibase without using any kind of package. I'm just going to apply the Naibase using the, I'm going to build the Naibase algorithm using the equation that we have discussed. As this is a 33 data, it is a little bit difficult for me to just call all the names and do. So I'm just going to take the first 4 column or 3 column. With respect to that, we will be building the Naibase algorithm, right? So, but before that, I'm just finding the class probability. Class probability, which is equal to data of diagnosis dot value counts of normalize equal to true. What is these two numbers? With respect to the equation that we have written for Naibase, can you tell in this equation?
P of M or P of B?
P of M and P of B, right? Okay. So in this equation, P of M talks about out of that whole data set, how many numbers are belongs to malignant. And here this probability talks about how many observations are belongs to benign. So this we have just did the value count, and if I put normalized equal to true, obviously it is giving me the numbers with respect to each class. So I'm just making this as P of M. So out of this, benign is okay. So P of B, which is equal to class prob of that first element 0, then P of M, which is equal to class probability of 1. So I have computed these two parameters which we required while we implementing the naive-Bayes equation. P of M and P of M and P of B we have computed. Fine. Now the next thing is I don't want all the columns. So what I'm doing is data, which is equal to data of, I'm just taking only okay, I'm just taking this diagnosis, radius mean, texture mean, perimeter mean, and area mean. Let it be. Only those things I'm just copy pasting here. Of course, I have to give this in quote. Right. So just for the simplicity, I'm just building my model with only 4 features. So if you feel like typing this as R, I'm just copy pasting this. So radius mean, texture mean, perimeter mean, area mean. With this 4 feature, I'm just going to apply the naive-Bayes. If you want to see this, you can see now only this 4 feature that I'm having. So now I'm just taking a data 1. In data 1, I'm just taking only the malignant part of or malignant observations. So data of diagnosis, which is equal to M, which is equal to M of data. So which means I'm just taking only the malignant information, malignant observations in data 1. Similarly, I'm just doing this for benign, and I'm just keeping that in data 2. So data 1 is a variable in which I have all the observation belongs to malignant class. In data 2, I have all the information belongs to benign class. I have copy pasted that. So what is the next step? Once I have taken malignant of M and malignant of B, then what is the next thing that I need to compute? What is the next thing I need to compute?
Conditional probability.
It's an likelihood. That is, conditional probability is my main aim. For that, I have to compute this likelihood, right? Here, this equation is changing like P of radius mean given malignant, P of area given malignant, P of perimeter given malignant. So like that, I have to find all those probability for each and every feature in the malignant group. For that, I have to find that distribution. I have to fit my data into that distribution and all those things I have to do. So for that, I'm just using that SciPy package from scipy.stats. I import scipy.stats as stats. Before that, let me just show you that data. Now I want data 1 of simply I'm plotting the KDE plot, right? So this is a kind of bell-shaped curve which has been plotted using that normal distribution equation only. Now, if I ask you for a radius mean of 15, what is the probability? What is your answer? If I ask you, like, for the radius mean of 15, what is the probability? How will you tell that?
Around 10.
Little bit more than 0.10.
Yeah. So it is like qualitatively means it's like we have to draw one vertical line from this 15, and we have to see at what point it is actually crossing my graph, and from there if I draw one line, that is actually the corresponding value, right? So that I can also calculate. This is just in terms of plot, I'm just showing that I can calculate from the package which is there in stats. So I can do like this, stats dot Gaussian KDE of data 1 of radius mean dot PDF of state 1. So if I give dot PDF of 12 will come somewhere here, no? 12 will come somewhere here. If I draw one line, it is around 0.033. It is 0.033, right? If I put 15, you will getting something like 0.105, just more than 0.105. So 15, if you draw one line, you will get something above this 0.10. So that is the reason why we are getting something like 0.105. So rather than seeing this graph and approximating that value or qualitatively understanding that probability value for the corresponding input level, if you use this Gaussian KDE function, you can easily compute it. Everyone got the meaning of this particular line, stats.gaussian.kde? Or no?
No, sir. Yes, sir.
No or yes?
No, sir.
See, I asked you what is the probability for the radius mean 15. So you people told like for the 15, the value is something more than 0.1. So by seeing this graph, you people approximated that. Now I'm telling that in SciPy statistics package, there is a function called Gaussian KDE. For that, if you give that column name and for what value you want to find the density or probability density value, if you give that using the method called dot PDF of 15, it will just plot your Gaussian kernel graph for this radius mean. In that graph, for that 15, for that value 15, what is the corresponding probability? That also it will give it to you.
Yes, sir. Got it.
Right. So now we have know how to find the corresponding probability value for any continuous number using the distribution. Using this distribution, this Gaussian KDE, it's actually doing that task for us. Now let us take some test input. Say, and just want to check what is my output for this. So np dot array of, I'm just giving some number 13.54, 14.36, 87.46, number say 566.3, right? So what is this 4 numbers? This 4 numbers corresponding to this 4 columns, input column: radius mean, texture mean, perimeter mean, area mean. So now I have given my radius mean is 13.54. And what is the second number? Texture mean is 14.36, and perimeter mean is 87, and area mean is 566. Now I'm just going to test for this particular test observation. What is my corresponding class, whether for this observation the class is malignant or class is benign. So that is what I'm just going to compute now. So for this, I'm just computing something so I'm just going to apply my base formula here. So my base formula is saying that I have to multiply all those likelihood. How can I find that likelihood? As here everything is a continuous variable. Stats dot Gaussian, the same thing. Here dot PDF of what is the value that I need to pass? What is the value that I need to pass?
The array of all the numbers.
Array of all the numbers, really?
13.5.
First one.
Yeah, the first one only, right? Because 4 likelihood will be there, no? If I expand, if I write the naive Bayes equation for this, the 4 likelihood, for that 4 likelihood only, I'm just using this function to find the probability. So PDF of test of 0, right? So you're not agreeing this? Yes or no?
Yes, sir.
Okay. Then multiplying for each of them.
Then I'm just going to write this, but now this column name I have to change with what? What is the second column? I think texture mean. Texture mean PDF of test of 1. Into the third one is perimeter mean. Perimeter mean is text of 2. The third number is actually perimeter mean. Then the last number is
So we can make it a multi-line.
let me make that. I'm just using this as say some name KD1. Into what? After all the likelihood, it is fine, or I need to multiply something else?
Probability of M.
Probability of M, we have it in which variable?
Diagonals. P underscore M.
So P underscore M. Right? So let me copy paste this.
I think.
Any mistake in this?
The braces needs to be added, I think.
Sorry?
I'm just checking, sir. Like I am getting some error.
Yeah.
The brackets should be. We have to enclose it with brackets.
PDF of here we have closed, no, Gaussian of something. Let me just run it for this one thing. It is correct only.
Sir, do Control Z. There one bracket was missing.
Where?
In
No, I think this is the index problem. If I
No, it works. Sir.
Yes, sir. If you
starting
put
bracket
the
is the
internal, then I think it will work.
No, you can put it. So you can put in that also.
Yeah, now it's in, right?
You can put this way also, sir. In multi-lines, you just need to put one starting bracket in the starting and one closing bracket in the end. You can put into multi-lines.
So here, second line?
Yeah, put one here and put one at the end. The parenthesis, not the square bracket.
Before this KDE?
No, after that equal to.
Before stats.
After the equal to, yeah. Start a bracket here and put one at the end. No, the
normal bracket.
Long bracket, sir. Down.
The parenthesis one. Yeah. And put one at the end, and you can put in multi-lines.
Now you can see it. So now,
Sir, actually, in last class, why did we do star DT?
sorry,
Uh,
star.
yeah, star DT.
That we have done. Say we have done the hyperparameter tuning. After doing the hyperparameter tuning, we can come up with some parameters for some features like max depth should be this, minimum sample leaf should be this, and estimator should be something for 4 or 5, 3 or 4 variables or 3 or 4 hyperparameters. We got that. Once again, if you want to develop a decision tree with that number that you got, rather than once again defining the decision tree classifier of and typing all those values, if you just put star of that basis base param, then that automatically that value will be assigned in the decision tree.
Okay, sir.
Say we have computed the decision tree. So generally we will be using the thing like decision tree of. That's it. Now I know what is that hyperparameters. So that hyperparameter I understood like for max depth, my model is for max depth 8, my model is doing well, and then minimum sample leaf. If it is 12, my model is doing well. For minimum sample split, if it is 30, my model is doing well. If a method is entropy, my model is doing well. Rather than typing all those things, all those numbers we have computed using this function. Say we have tuned my model dt dot best param. Best params will give all those numbers. So rather than typing this by seeing the best param, once again typing this, if you just put star type underscore dt, automatically whatever the parameter that we computed, with this parameter my decision tree will be reassigned.
Okay, sir.
Right? You can also use directly best estimator. dt your parameter dot best estimator, that is also the function. Straight away you can also use that, and you can move that into a variable. So you can do it in multiple ways. And then typing it to save the time, I have passed like that. So similarly, can you do for KDE2? That is, I want this same inferences for benign class. For benign class means what is the thing that I need to change here?
P underscore B instead of P underscore M.
Okay, P underscore B, and one more thing. What is data 1 here?
Data 2.
Yeah,
data 2 and then P underscore B.
Yeah, data 2. That is the other group of data. That is the benign group. For the benign group, once again I am finding this and then this making this as estimation 2, KDE2. Right? Simply I'm just writing one condition like if KDE1 is greater than KDE2, then what I have to print? What I have to print?
Malignant, yeah.
The input sample belongs to
class 1.
malignant. Else it is benign. So what we are getting? So with this number, we are getting like the input sample is belongs to benign. The input sample is belongs to benign. Just see what is your KDE1 value and KDE2 value. So it does not look like a probability, right? It is like KDE1 and KDE2 values giving you the probability numbers here. Yes or no?
It's not probability.
Sorry?
No, we're not calculating probability, right? Just we are taking the numerator.
Yeah, we are taking that numerator. We are not actually taking the denominator. But anyway, that proportionality will remain same, right? As the denominator is actually same for both those equations. As denominator is same for both those equations. So definitely by seeing these two numbers magnitude alone, if KDE1 is more than the KDE2, then we can make that decision as malignant. If not, we can take the decision as benign. Here it is 3.2 into 10 to the power of minus 9. So 3.2 10 to the power of minus 9 is actually less than 4.47 into 10 to the power of minus 7. So obviously your KDE2 is here high. That is the reason why it is printing as benign. But if I want to see the probability value, then I can do something like this. KDE1 plus or KDE1 divided by KDE1 plus KDE2. So this is the probability that it belongs to probability that it belongs to malignant. Similarly, if I compute this, like KDE2 divided by KDE1 plus KDE2, then this is the probability belongs to benign. So now it is probability, right? Because if you add these two numbers, you are getting 1. If you add these two numbers, you are getting 1. So exactly, even if you want in terms of probability, you can do like this by adding this numerator plus the denominator and use that as an overall denominator for each and every element. So KDE1 divided by KDE1 plus KDE2 or KDE2 divided by KDE1 plus KDE2 will actually gives you the exact probability. So if you want to talk in terms of probability, like what is the chance that this particular observation belongs to this class, you can do a kind of a quick normalization like this, so that you can also speak in terms of probability while you are mapping your input to the output. Understood? So I have explained the concept of naive in a classification sense, and we have whatever the equation that we have executed or we have discussed, for which I have written the code without using any function, and we ended up with the result, or we are actually made our base algorithm to make the classification decisions. Any doubt in this?
Sir, one doubt here. What do we mean by this input sample belongs to benign? That means like in decision tree we ignored the like non-dominant part. Is it in that way we are saying, or?
No. So that input sample is, this is what my input sample. Right. So I have my whole data. This is the data, the whole data. I have it in data like 4 column of information, and along with that 1 output column. So from that I'm just doing this calculation, but I'm doing this calculation with respect to this one test input. Say one new test input is coming for that the radius mean is 13, texture mean is 54, and perimeter mean is 87, and area mean is 566. Now for this number, what is the class? Whether for any input observation with this 4 numbers is belongs to malignant class or it is belongs to benign class. So for that, I'm just applying this number into that base equation. So on computing all those likelihood and using those product of all those likelihood and prior probability, I'm finding the probability, finding the conditional probability with respect to malignant class and with respect to the benign class, and I'm just making the decision if KDE1 is greater than KDE2. What is KDE1? KDE1 I have computed using these 4 numbers for the malignant group. If you see data 1, data 1, data 1, data 1, I have used. What is data 1? Data 1 is the section of the malignant data, right? I have filtered my whole data with respect to only malignant classes. So on that malignant class distribution function, I'm just fitting this data, and with respect to that, I'm finding one probability. If this probability is more than KDE, I'm just making the decision like it is belongs to malignant class. If this KDE2 is greater than KDE1, then I'm making that decision like it belongs to the benign class. So that is what here I have written, that input sample is benign, belongs to malignant because KDE1 is greater than KDE2. Got the point?
Yes. So based on the previous data set, we are taking the test sample and validating whether it is malignant or benign using this formula, right?
Yes, it is based upon the previous data. We are taking this test sample. Test sample can be new. Test sample can be new, but whatever the column that we have in our train data, that column only we can take it as a test sample. For any number, we can go for that. But that number we are actually fitting in the distribution. So this is the distribution. In this distribution, we are actually computing or plotting with respect to our past data, the data that we have in our hand. That is nothing but your train data. So in this data that we have in our hand, we are fitting this new input and we are seeing what is the probability.
Okay, sir, got it.
Yeah. Harinath, what if the condition where the KDs are equal? Yeah, of course, chi is there in the sense, say generally in machine learning, whenever you do classification, if chi is there, so say if you think with respect to the big data set with multiple column, definitely this probability you won't get it as exactly 50-50, but still if you are getting something like 0.5 0.5, then people will go with the majority decision. Say in your data set, out of that 1000 data, 700 data are belongs to benign, 300 data are belongs to malignant. Then all your SQL functions will see this count, and with respect to that count, it will make the decision. Let us say if a malignant count is less and benign count is more in your whole data set, then obviously if tie happens, then that test sample will put under that majority class. Say here in the majority class is benign means that for the tie observation, the class is benign. Got the point? But it will rarely happen, especially in A-base, it won't happen at all. But of course, in KNN it may happen. While it's in KNN, while it's this kind of tie happens, then it actually go and check the count information of your output. So which level is more, that test sample will be allotted to that particular level. You got the point, Harinath? Yeah. Of course, there is other ways in KNN to control that. We will be discussing that. But anyway, so this is kind of regular approach it is using whenever tie happens.
So we can take threshold, right, for KD1 and KD2. Say here KD2 is a 99%. So if it is a 60% or 7%, we can take the threshold, right? If it is the 70% of malignant, then we can tell malignant. Otherwise, it is the benign. We can put the condition also, right? Not like 50-50, like 70-30.
Yeah, that's true. Say that is playing with threshold that we already saw. But anyway, SQL will always see this with respect to 0.5 threshold. So that is say 50%. Say if what his question is, if both are 0.5, KDE1 and KDE2 are exactly equal, then what kind of decision? Because here I have written only two conditions. No, if KDE is greater than KDE2. Else means KDE2 is less than KDE1. That is the another class. But he is asking like, what if I do if KDE1 is exactly equal to KDE2? What if probability of malignant is 0.5 and also probability of benign is 0.5? So that is his question.
Yeah, okay, sir. Thank you.
Fine. So now, quickly, let me show you one another. Let us discuss.
For many input variables, how to calculate? Like we'll be typing all.
No. That is what I'm going to show you. That is a function. Say in one single line you can do. Say let me show that. So then I will go to that. From sklearn dot base import Gaussian NB GNB, which is equal to Gaussian NB of GNB dot split of the data. Of course, you need to split your data into input and output. And also, if you want, you have to split that as a train and test. Quickly, we can do that. Input is equal to data or output, which is equal to data of diagnosis. Input, which is equal to data dot diagnosis, comma 1. And if you want, you can also split this from sklearn dot model trying to split. Right, so what happened? So I have split my data into X-train. So here I'm just going to fit my Gaussian A-based model with X-train and Y-train, and I'm just going to predict the Y-pred, which is equal to GNB dot predict of your Y test. Generally, it will handle X-train, Y-train, X-test, Y-test. Check. Okay. So you people are also getting this error, because generally more than two level only we have to convert it. Otherwise, by default, it have the ability to handle this. Anyway, let me convert this m into 1 out equal to out dot replace of.
So you don't handle categorical.
Sorry.
Should we convert it to 0 and 1?
Yes, that is what I'm doing. But generally, for a binary class, it will do that by its own. Update. Something else is going on. Sorry, what is a mistake? I have made one blind mistake. No one noticed that. What is the mistake that I have made? Here in the implementation, dot predict, what I given?
Y test.
Is that Y test I need to pass?
X test.
X test, right?
Yes, no. So say if you have only binary class, that is say only 2 levels in your output, all your sklearn machine learning models have the ability to print your results with respect to that class label. Even though that class label is in string, it has the ability to handle it. If there is more than 2 class, then you have to convert that into some kind of number level. Otherwise, you can leave even as it is. You don't need to even convert that malignant as 1 and benign as 0. It will handle it. Any text information in the input side only, it won't handle. Output side, if you have the label information as a text in your output column, your sklearn will have the ability to handle it, right, by its own. So sklearn dot metrics report classification report print classification report of whitest comma white. So this is the result that we are getting for this data using the Navies, right? So whatever the thing that we have done now has been happened in a much optimized way by this Gaussian Navies function, but the approach is same. The underlying approaches are very much same as we have implemented in a raw way. But anyway, we can't do that for a big data, right? Again, we can't type all those lines and doing all those stuff is meaningless. Of course, you can write your customized function for it. But anyway, such a kind of optimized, customized function is available under this sklearn function, and we can use it. So my objective is, if I directly use this, I have nothing to explain, right? So that is the reason why I have just explained the concept, and then I have implemented that without using this, so that even if you have any kind of queries or a kind of doubts during our explanation, I hope that could have been clarified while we are implementing this logic in a raw way in Python. Then this is the way that we can implement that in sklearn. Right? Now, with this, let me explain one another famous used case for Naibase. So Naibase is one algorithm people will actually generally use in text analytics. So even though our objective is not to study the text analytics in detail, let me quickly explain you or do some kind of workout so that you can easily understand how this Naibase concept has been used field of text analytics to make some kind of classification result for the text data. Now say I'm just using some input like a great game, the election was over, very clean match, a clean but unforgettable game. Then it was a close election, right? Let's say. So these are all the four statements. So I'm just going to build some model to classify this statement, into two categories. Say this category is sports, this is not sports, Again, this is sports. This is sports. And this is not sports. Right? So I'm just going to build the machine learning model to make my machine to understand whether this particular statement or whether this particular string of information is related to sports or not. Right? So for that, we have to make this unstructured data. This is actually an unstructured data. We have to make this unstructured data as a structured one. So how can I make this unstructured data as a structural one? I have to do the counts. So this is different concepts like vectorization and all those things people will do. There are so many pre-processing that you need to before extracting the word. But anyway, let it keep simple. Just can you tell how many unique words are there in this 5 sentences? Can you tell me how many unique words are there in this 5 sentences?
Game, election, match. That's.
So shall we write otherwise? The screen will. Let me write here.
13.
16.
Word is
15, I think.
Great. So just we can take only the proper word. Forget about the articles, preposition, and all those things. Right? So only the proper verb, noun, adjective. These things we can take. So great.
Game.
Yeah.
Election. Over.
Yeah. Just hold on. You just tell me. Great. The word great, how many times exists in the sports and how many times exists in the non-sports?
One time and
1 and 0.
Sports, 0 in non-sport.
1 and 0. Then the next proper word is game. Game, how many times exists in sports and how many times exists in non-sports?
2 and 0.
2 and 0. Then the next word is election.
Match.
Just eliminating the election. Election
0-2.
0-2.
0-2, huh?
Yes.
Yeah.
Fine. Then over.
Match.
How many
1 and 0.
over?
1 and 0.
0-1.
0-1.
Non-sports it is 1. Okay. Then very
Clean.
Very
1-0.
1-0.
1-0. Clean
1-0. What? I mean, sorry. 2-0.
2-0. Then it I can eliminate. But I can eliminate. Forget
Match.
about
Match.
Match is important. Match 1-0.
1-0.
1-0. Then clean unforgettable.
One zero.
Unforgettable is 1-0. Game we already written here.
Close.
Was close also no. Okay, close. Close is
0-1.
0-1.
Election we have already written here. So after removing some kind of unwanted words in text analytics, people will call these words as a stop words, right? So there are some kind of libraries and other things, or you can write the customized function to remove those stop words. But anyway, so after removing all those unwanted stop words or more adjectives or some articles, preposition, all those things, we have only 1, 2, 3, 4, 5, 6, 7, 8, 9 kind of keywords, and we have its frequency count information for each class. Now my question is, let me erase this because as we already have. Okay, let me first write here. say one new statement is coming like a very close game. What is its class? So now we have some data, and for from that data we have actually counted the distribution of each and every word across different classes. Using this information, I'm just going to find what is the probability for this particular statement to be in sports or to be in non-sports.
Should be in sports.
Yeah, should be sports. But tell me that probability. Tell me that probability using base. Apply base and tell me.
0.75.
425.
Shall we write that equation? So can anyone tell what is this first element? What is the first likelihood? P of
very given sports.
So I have to say for each and every word, what is the probability I can compute, right? So here there is what is the probability of grade to occur in sports? What is the probability of grade to occur in sports? If you count all those words, totally how many keywords there in sports and how many keywords in non-sports? So
7 and
out of these total words, how many words actually, how many total words is there in sports? So 2 plus 2, 4, 6, 7, 8, 9. 9, right?
8.
8, sir. 8.
8.
8.
8.
8.
8.
Then clean must be 1, huh? Whether the screen count is 2 or 1?
2.
It is
Very
2.
clean match and a clean button.
Third and fourth 2 times, yeah.
Sorry?
In third and fourth we have 2 times, sir, right? Clean.
Clean.
Very clean,
8.
but unforgettable game. Clean is
then now so then 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 2 is 6, 7, 8, no?
Yeah. 8, 4.
Here 2 plus 1, 3, 4. Right? So now if I ask you what is the probability of grade to occur in sports, you will tell 1 divided by 8, right?
1
What
by
is the
8.
probability of what is the probability of grade
12.5.
sports? You will tell 2 divided by 8. Similarly, what is the probability of clean to occur in sports? You will tell 2 divided by 8. So now similarly, I need to find for this statement what is the probability of vary to occur in sports.
1 by 8.
What is the probability of flows to occur in sports? And what is the probability of game to occur in sports? If I compute this probability, what is the probability of vary to occur in sports by using this table? We can tell 1 divided by 8 into what is the probability of flows to occur in sports? 0.
That is
Then what is the probability of game to occur in sports?
2 by 8. 2 by 8.
2 by 8. Right. So even though 2 by 8 is a maximum kind of probability here, if you see in this distribution count, the 2 is the maximum count. Yeah. So one element is having that 2 divided by 8 probability. So almost game is there. Right, but still, because one number is becoming completely 0, that whole probability is going with 0. So this problem always happen in text analytics. Are you agreeing this? Because whatever the whatever the data set that they are having, you may just go and type some kind of word that people generally won't use at all in that particular domain. So whatever the different reviews or whatever the different statements that they have collected in that particular domain, with respect to that only they will frame this kind of table. Now you are writing some review in a kind of English, say that kind of word generally people never used, then obviously the count may 0, right? So even though there are so many other common words which is actually matching your statement with that particular domain statement, as 1 or 2 words you are actually newly using, because of that, that overall probability may become 0. So this is a kind of issue that always occur in text analytics. So in order to avoid this, what they will do, they will call some process called Laplacian smoothing. So simply they will add 1 with all those numbers. So they will overcome this problem of some word going to 0. Some word count going to 0. So here total, now here total is how much? Total is how much with respect to this?
17.
17.
17?
Yeah.
And here?
13.
It's 13.
11. Oh, sorry. No, 14. It's 14.
14 or what? 14?
No. It's 13. 13. Not 14.
Give me the number. 1, 2, here it is 3.
13.
13.
7, 8, 9, 10, 11, 13. So 13. So now you have to adjust this probability. So now what is the probability for sports? What is the probability for sports? What is the probability?
2 by 17.
2 by 17.
2 by 17.
The count is now 1 by 1. The total count is 17. So it is now become 2 by 17. Now this will actually will become
1 by 17.
1 by 17.
1 by 17.
3 by
It will now
17.
become 3 by 17. So now we are not having this problem of getting one probability to 0. So now similarly, we have to do this for the other class. So this is for probability of sports for a given state.
We just added 1 to everything, or
Sorry?
So can you just, we just added everything plus 1, or?
Yeah, we have added 1 with all the count. Already we have the count information for each and every word. We are just adding 1 with all the count. So obviously that all the 0 count now will become at least now get a value at least as 1. So we won't get some probability as 0 while we are in while we are substituting that in our main equation.
Sure.
Right. So now probability of non-sports for a given statement. For a given statement is probability of very non-sports into probability of close non-sports into probability of game non-sports. Of course, here I missed one another element. What is that?
Pure sports.
Yes. Probability of sports.
Sports.
How much that is?
Oh, 17 by 30.
Hmm?
17 by 30.
17 by 30?
1 by 2.
30. 30.
3 by 5, sir.
3 by 5. How you are telling it's 3 by 5? Even you
No. I think 17 by 34.
30, right? Both are 30. 17 plus 13 is the 30.
8 by 12, right, sir? It will be 8 by 12, right?
No, we are considering 17 and 13. So 17 by 17 plus 13. So there is a probability of sports.
Oh, sorry. Yeah.
Only the probability of sports will be 17. It will be like 1.
So you are telling like 17 divided by 17 plus
13.
Right, you can also calculate like this, but as this is a repetitive, definitely zero problem and all won't happen here. You can also see how many unique words are there in sports. How many unique words are there in sports?
8.
8.
1, 2, 3, 4, 5, 6. Only 6 unique words, right?
6 words.
6 unique words only is there
6,
in
yeah.
sports, right?
Yeah, 6.
So out of totally how many words are there? Totally how many unique words are there?
9.
9.
6 by 9.
So 6 by
1
9.
by 30.
So that also you can use. But anyway, proportionally it will be remain same only, no? So proportionally it will be remain.
Yeah.
So
Just we're adding 1.
yes. So like that you have to compute for this also, so that you will get the, say here that P of very divided by non-sports is nothing but again 1 divided by 13. Here it is actually 1 divided by 13 into P of close divided by non-sports. Close how many times is coming? 2 times. So 2 divided by 13. Game how many times is coming? Obviously only 1 time. 1 divided by 13 into 13 divided by 17 plus 13. So like that you have to do that calculation, and by seeing these two numbers, which number is having the high value, you have to allot that particular particular observation or that particular statement to that corresponding class. So if you see the same equation, whether in the previous case while we computed the cancer, or in this case we have computed or we have applied this concept towards the text analytics, the concept remains same. The concept remains same, that the way that we have to apply the Bayes rule, that actually remains same. The only thing is the data. So previously in that cancerous case, all my input variables are kind of continuous numeric. So for that, I have used the Gaussian kernel distribution function, and based upon that, I will get that probability. Here, all those values are just a frequency count, how many times one particular word exists. Using that, I can directly calculate the probability, and I can use that in my likelihood positions of my Bayes equation. So this is the another classic example where we can use Bayes. Right, for structural data, generally for a continuous data, as we know that the data are not very perfectly normally distributed, but that Bayes theorem is the Naive Gaussian Naive that we have used is assuming that the data is normally distributed. With respect to that only, it is actually computing all those numbers. But that is the reason why that Gaussian Naive the results may little bit deviate compared to other machine learning models for a kind of continuous data. For this kind of discrete data, this kind of whenever you have a count kind of information, here it is a frequency count, right? How many times each and every word exists. So whenever you have this kind of data, and for which compared to other algorithms, other nonlinear algorithm, your naive.
Welcome to Racket.
Sorry. Any question?
No, sir.
Yeah.
No, no.
Yeah. So for such a kind of whenever your data is in terms of frequency count, then obviously this Gaussian this Naive will work well. But there are some variants. So whenever you have a data like this in a structural way, like say this is observation 1. For observation 1, we have a data like this is word 1, word 2, word 3, word 4, word 5, word 6. Always your text analytics data are very wide, because so many data that we can, so many words that we can extract after we analyze all the statements. Here it's only 5 statements and also very small statement. For that itself, we will end up with around 9 discrete unique words. But imagine if you are comparing different reviews and all, so definitely you will get so many discrete words. So say this is for the second observation, third observation, fourth observation. These are all kind of review. So say I can even consider this as review 1, review 2, review 3, review 4 for each and every person. So in this review 1, how many times this word has been used? Say 5 times this word has been used. This word has been used only 1 time. This word is not at all used. This word is not at all used. This word is used 2 times. This word is used 1 time. So always while you are constructing some kind of data like this, you will be getting kind of frequency count information. Whenever you are extracting some data from your text analytics or any text, any essay, any review, any status, any tweets, you will be getting this kind of frequency count. So whenever you have a frequency count information like this, then you can go with an multinomial naive Bayes. Multinomial naive Bayes. And whenever you have a continuous data, whenever the continuous data, the previous example that we have did know, we have radius mean, perimeter mean, area mean, all those values are continuous information. Whenever we have a continuous information, then we will be going with Gaussian. Whenever we have a frequency count information, then we will be go with the multinomial. And whenever we have a binary information, like the same data, like word 1, word 2, word 3, word 4, and this is for review 1 or statement 1, review 2 or statement 2, review 3. I'm just making my data like whether this particular word exists in this review or not. So it is exist, this is not exist, this is not exist, this is exist. Whenever I have a data set like this, which actually talks about whether that particular information is exist or not, whether this particular word is exist in that review or not. Whenever a data set is having only zeros and ones in it, then I have to use Bernoulli naive Bayes for it. Bernoulli naive Bayes. So there is 3 variant: multinomial naive Bayes, Bernoulli naive Bayes, and Gaussian naive Bayes. Gaussian naive Bayes we will be going with whenever our data is continuous, and multinomial naive Bayes we will be going with whenever our data is actually having the frequency count information, and Bernoulli naive Bayes we will be going whenever our data is actually Boolean. But of course, multinomial naive Bayes only is having lot of essence, especially with respect to the text analytics. We will be applying this multinomial naive Bayes more frequently on the text data to get the good performance out of it. But anyway, Gaussian naive Bayes, as I told, we will be using as a kind of a base model, because all other models that we discussed, like decision tree, logistic regression, on the models that we are going to discuss in our coming classes, like random forest boosting, always have the ability to provide better result with respect to the Gaussian naive Bayes, because Gaussian naive Bayes is working with an assumption of the data is actually normally distributed. So the more your data is moved from the normal distribution, obviously we will be getting the kind of poor results with respect to the Gaussian naive Bayes. Right? Yeah, of course, Raghu, we can take one short break at this point. Any doubt?
So multinomial naive Bayes.
Multinomial naive Bayes is for frequency count information, as we didn't know now with respect to that text statement. So whenever you have a kind of text statement or text data with you, and if you do some kind of pre-processing, then you will be get the frequency count information only, like how many words exist in this, how many time good exist in this first statement, how many times bad exist in this first statement, how many times hype exists in this first statement, how many times lottery exists in this first statement. If you extracted your data like that, then your data set will have a frequency count information only in each and every cell, as I told here. So how many times this word 1 exists in this first review, how many times this word 2 exists in this first review, how many times this word 3 exists in this first review. So if you consolidate your data like this, definitely each and every cell in your data set will have some frequency count information. Whenever you have a data set which is filled with some frequency count information, your multinomial naive Bayes will give you the better result.
Yes.
Sir, one doubt here. So when the data is a mixture of Gaussian and this Bernoulli, so in that case,
Yeah, that is actually in sklearn there is no way to handle it, right? But if you see, there is some third party functions are there, but which is not there in sklearn. Mixed Gaussian models are there, right? You can use that mixed Gaussian models, and you have to inspect like these are all category. These are all for this. These are all the binary, and these are all the continuous. These are all the frequency count. If you mention like while you are defining that algorithm itself, if you mention like it, then it will actually appropriately apply different strategy, and it will combine all those results, and it will give you the overall probability. But sklearn is not actually providing that option as of now.
Yeah.
Sir, one doubt. So in naive Bayes, when like we were when we want to find that probability of a continuous, we were considering that as a like normally distributed and use that probability, right?
Yes.
So if it is not normally, do we have to make transformation before we start, or because in
Yes.
our example we saw it was bimodal, it was not a normal, right?
No, it is not bimodal means say we are on the normal distribution we are seeing with respect to that data only. We are not actually comparing with that output column and all. Say radius mean is some continuous number, no, from some low value to high value. If I plot that, whether it is actually giving me a normal distribution or not. If it is not actually normal distribution, you can also do some kind of transformation and make that to be a normal distributed one. Then only you can really get the good results from your Gaussian Bayes model. If it is not normally distributed, it is actually deviated much from the normal distribution result, then obviously your Gaussian models will provide the poor results.
Okay, that should be like part of pre-processing.
Yes, of course. You have to do pre-processing. Otherwise, you can move to some other nonlinear model. Of course, the only pre-processing that you can do is you can treat the outlier and you can try with some transformation. So that actually makes your data close to normal distribution. So once it is close to normal distribution, then you can trust the naive Bayes because it's a simple model. With that simple model itself, you are getting the reasonable output in the sense it's well and good. But still, if you are not able to bring this close to normal distribution, obviously you have to think of option of going with some other machine learning models.
Okay, thanks.
Yeah.
Dr.
Can you please share
Senthil, shall
the
I?
job?
Yeah.
Can you please share the notebook of what we have done so far?
Yes, I will share.
Okay, thank you.
Dr. Senthil, shall I load the poll questions?
That first two question alone, can you load, Nina?
Yeah. The first question, Dr. Senthil, it's not fitting in because the words have exceeded.
Okay.
So shall I put it in the chat so that students, it will be helpful for students also. Yeah.
Yes.
Ma'am, can we take after the break that?
Sure, definitely.
Ma'am, for the second question, what you have put in the chat, so where we need to give answer for that? We can privately ping you or
to Dr. Senthil Abhishek.
sorry?
To sir, you can ping privately. You can ping sir the answer.
Lena, is it that answers also too long to fit into that cell?
The number of words were exceeding, so I tried to make it small, but still it was.
Yeah, but the question is a little bit big, but that 4 options are small only, no?
Yeah, the options were fitting, sir,
Then,
but
then only half of the question, as long as it's fitting, we can put it in the question, right? So that full question we can give it here in chat so that they can give the option there. It's because here we can't consolidate the total count, right? If it's not required, then it is fine. I'm just saying it.
Yeah.
Lena ma'am, I'm able to see only chat. I'm unable to see poll.
so you want me to add it in the poll, is it? This question?
No, fine. Then it's look like there is only one question, right? So anyway, we are going to release one another poll at the end. But anyway, so even though it is not fully fit into it, we can just put the half of the question there. That full question we can give it to them in chat window so that they can study the question here in chat window, but they can answer there, no?
Sure, definitely. So then, fine, sir. I'll add it in the poll at the second poll that we do. No, in that time I'll add it.
Okay.
Yeah, Maheshwari. Yeah. Only one question, Maheshwari, now in the poll.
So for second, should we have to give the answer or wait for second poll?
Please wait till the second poll, Vinayak.
Okay, thank you.
Yeah, thanks.
Fine, shall we start? Is everyone back?
I got only 24 responses, sir.
Okay. We'll wait for 1 more minute. Lina, shall we start now?
Sure, sir. Sure. I have ended the polling and I have shared the results, sir. 41% have answered the first option, 0.213. 38% have answered the second option, and 13% the third option, that is 0.45, and 9% last option, 0.62.
Let me see that question.
So what would be the P of X here?
So here, the number of input is only one, right? Sorry, here the number of input is actually, the question is, I have given the probability of defaulter as 0.45 and probability of non-defaulter as 0.45, which is actually your prior probabilities. And P of male is 0.5 and P of private employee is 0.55. And also we have given like P of a male with a condition defaulter is 0.2 and probability of private employee given defaulter is 0.65. So all the elements in the bias formula has been directly given to you. So that P of X is actually, you have to consider by seeing that these are all independent. You have to consider the product of your P of male and P of private employee. Got the point? Generally, while we do our calculation, we have not calculated this P of X. As this is a denominator, we are going to make the decision and we are going to calculate this probability for both the classes. We are not actually calculated that P of X, but provided that if it is actually independent, all those that is an ABS is making that assumptions always, right? So the input features are independent. So the P of X is nothing but your probability of your inputs. That is the evidence. So here the two inputs are gender is equal to male and the is a private employee. So for that, individual probability has been given, like P of male is 0.5 and P of private employee is 0.55. So that should be your denominator. So any other doubt in that solving that problem? Every value is straightforward there, right? Yes or no?
Yes.
Yes, sir.
So all the values are straightforward. The only thing is, while we do P of X, we are not actually expanded, or P of X, we are not actually bring in that equation. We just used to compute only the numerator, because generally we used to compute that probability for both the classes. For both the classes, that denominator P of X is common, so generally we won't compute that. But anyway, here with respect to one class only they have asked. So in that sense, whatever that probability that they have given for each and every input level, that we have to use there in the denominator. So the answer, if you substitute all those values in that Bayes formula, you will be getting as 0.213. Precisely, if I say, it is like 0.2 into 0.65 into 0.45, the whole divided by 0.5 into 0.55. So that is the expression. So if you compute that expression, then you will be getting that 0.213 as an answer. Fine. So the other question, once again, we will release at the end along with two more questions with KNN. Let me share my screen. Fine. So the next algorithm that we are going to discuss is
Sir, just one question. So, Lina ma'am, so are we uploading these files what sir is saving? I mean, our Olympus?
Yes, yes, definitely.
Okay.
All the files have been uploaded except for today what sir sent in the session.
Okay. Thanks.
fine. Yeah, the next algorithm that we are going to discuss in today's session is KNN. So K nearest neighbor. So did we use any kind of imputer as KNN during our SLR session?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So just I may explain that in a brief way without going deep into the math of it, because at that point of time our focus will be on discussing the linear regression aspect. So, but anyway, whenever there is a missing value, the KNN will actually play a good role there to fill these missing values. So here in today's session, we are going to analyze this K nearest neighbor algorithm in detail in the perspective of classification. So it is actually a distance-based algorithm. KNN is an distance-based algorithm. So basically, the difference between one observation and another observation, it will calculate. So people will generally call that as proximity measure. Right? So difference between two observations. Right? So this proximity measures can be a similarity measure, or it could be dissimilarity measure. The proximity measure can be similarity measure or dissimilarity measure. Say I'm just finding the difference between two observations. I can find in a way how similar these two observations are, or I can find in a way how dissimilar these two observations are. Of course, both actually giving you the same sense, but some measures will actually give you the difference between two observations as a similarity measure. Some measures will give the difference between two observations as dissimilarity measure. Say, for example, if similarity is high means, what is your take on the difference between these two observations? You are finding the difference between these two observations that you are measuring in terms of similarity, and similarity is coming high, then what your take? What you
Difference is low.
Both are same.
Highly correlated.
Yeah, both are same. So both are actually very close to each other, right? So in some domain like recommendation systems, people will use the similarity measure, cosine similarity. If cosine similarity is 1, that is cos of the difference between the two observation is 1, then it means at what time cos will become 1? Cos of which angle is 1?
Cos 0, 1.
Cos 0, 1. Say if I have two measures, say this is one feature 1 and this is my feature 2, then obviously feature 1 and feature 2 are in the same direction. Feature 1 and feature 1 are in the same, are almost in line with each other. In this kind of situation, I will find the similarity in terms of cosine means. I will get something like cos of 0, the angle between these two is actually 0. So cos of 0, I will get 1. So that I understand this feature F1, this feature F2, or say rather than feature, this I will keep it as observation 2 and observation 1. So this observation 1 and observation 2 are almost close to each other, are perfectly close to each other. That I can understand if the similarity measure is close to 1. So whenever I'm measuring anything in terms of similarity, I want that value to be high to comment like these two observations are same. Similarly, in terms of dissimilarity, say dissimilarity measures, the classic example is distance. Distance, yeah. If distance is high, what is your take?
Both are different.
Difference between the two observation, and I'm getting the distance as very high, then it means these two are actually different data. These two observations are belongs to different class. Say if distance is low, if distance is very low, then it belongs to same class. Same class. If it is high, then it is belongs to different class, right? So whenever I want to compare two observations, I can compare through some similarity measure, I can compare through some dissimilarity measures. So all the distance based methods are kind of dissimilarity measures. So there are so many distance. While I'm saying distance, there are so many ways I can find the distance between two observations. There are so many ways I can find the distance between two observations. So even though there are so many distance, let me write one distance equation, and with that we will be actually defining the other distance equations. So say summation of I equal to 1 to n xi minus yi the whole power p. So this distance equation is known as Minkowski distance. This distance equation is known as Minkowski distance. So this is a kind of general template equation for distance. So by varying different values for p in this equation, we also model this as some other different distance equation. So generally, this is a kind of structure for the distance equation. This distance equation with p, we will be calling as Minkowski distance. In place of p, if I take 2, in place of p, if I take 2, then it becomes square root. So 2, by default, we can understand this as a square root. Summation of I equal to 1 to n xi minus yi whole square, right? So obviously this equation is known as Euclidean distance, right? So this distance equation, when p equal to 2, the Minkowski distance will become Euclidean distance. Similarly, substitute p equal to 1. When we substitute p equal to 1, what happened to the square root?
Will not have square root, sir.
So we no need square root.
No
So,
square root.
right, so 1 divided by 1. So there is no need of square root. When p equal to 1, the equation will become like I equal to 1 to n xi minus yi. So this equation, we are going to call it as Manhattan equation. Say I have 2 points in the plane. Right? Say I have 1 point here, and I have 1 point here. Say what would be, say this is 1, say this is 3. This could be 1, 3. Say this is 3 and this is 1. This could be 3, 1. Right? Say this is an x-axis. Say this is an y-axis. This is 1. So if I find, say this point is 1, 3, this point is 3, 1. If I put this formula in this Euclidean distance equation, if I put this numbers in that Euclidean distance formula, I will get one number, no? Can you tell that number is the magnitude of which part of this plane? Any idea?
Which part means?
Which part means, say,
Quadrant.
First quadrant.
First quadrant. See, the thing is, say, if I calculate, anyway, let me tell that. Say, if you calculate the Euclidean distance with respect to these numbers. So, how can I calculate the Euclidean distance with respect to this number? So,
root over x2, 3 minus
x1 whole square.
3 minus 1, the whole square, or typically writing, it is 1 minus 3 the whole square plus 3 minus
3
1.
minus 1 whole square.
If I compute this number, you will get on magnitude, no? That magnitude is nothing but the length of this line. Let me draw that properly. So just assume that it's a straight line, even though it's a kind of curve. I'm drawing it some as a curve. The length of this, if you connect these 2 points in a plane, you will get some kind of height, or you will get, if you measure this length is equal to this distance. This length of that line that you are connecting, that you are getting by connecting these 2 points, is equal to that Euclidean distance value. Similarly, if I put a horizontal line and vertical line with respect to these 2 points, what is the height of this part? How much?
3.
2.
Oh, sorry.
And this is 2.
Here?
2.
Can you put those value in Manhattan distance, and can you tell me the value? Manhattan distance.
Root 8. Root 8 it is.
So 1 minus 3 absolute plus 3 minus 1 absolute. So the value is 4, right? So if you simply add, say if you want to reach from this point to this point, if you travel in this shortest path, then that is actually Euclidean distance. If you travel in this way, then that total distance covered is given by your Manhattan distance. So Manhattan distance is also known as city block distance. Because if you see, in order to, from going to this point, rather than traveling in a diagonal way, a Manhattan distance is going in an horizontal way, vertical way, then again it's going in a horizontal way. So again it will go in a vertical way, horizontal way, vertical way, horizontal way, like that only it will go in order to reach any point. So that is the reason why your Manhattan distance is also known as city block distance. So Manhattan distance will give you the maximum distance between 2 points. Whereas Euclidean distance will give you the kind of optimized distance between these 2 points, right? So generally we will be using the Euclidean distance only to find the distance between 2 observations. Based upon that, we will be taking the decision about whether these 2 observations are close to each other or not. But anyway, as an hyperparameter, you can also play with this p. You can also play with this p, and for which value of p your model is actually giving you the better accuracy or better results in terms of precision, recall score, all those things you can analyze. So this p in your Minkowski distance is actually an hyperparameter. For different value of p, your machine learning model will tend to give the different performance. But anyway, the famous distance measures are Euclidean and Manhattan, and Euclidean is actually giving the kind of shortest distance between the 2 points, whereas Manhattan is giving you the maximum distance between the 2 points. Apart from that, there is something called Chebyshev distance. Again, Chebyshev distance is actually giving you the maximum distance for each and every feature. Let us see that later, because Chebyshev distance anyway, that's a kind of theoretical distance we are not really going to use for our machine learning models, and also sklearn doesn't have that Chebyshev as an distance measure in any of those packages. So it has Euclidean measure, it has a Manhattan measure, and also it has this Minkowski. So it has this general equation for Minkowski, and you can control this Minkowski for different value of p. So that any distance, if you want to achieve Euclidean distance, you have to use the Minkowski with p equal to 2. If you want Manhattan distance, then you have to use the Minkowski distance with p equal to 1. So if you want to explore your model for some kind of higher order distances, then you have to use the p value greater than 2 also and see your results. And if for that data set, if you feel like higher p value is giving the good classification results, then you can freeze that p value as your model's final value or model's final hyperparameter, so that you can build your model, so that you can deploy your final model with that corresponding p.
So p equal to 3 is the for a higher dimension, like p equal to 2 is the for 2-dimensional, right?
No. So please don't understand like that because of this xi and yi. Say, let me
No. When we use p equal to 3 and 4, so
no, it is not 3-dimension, 4-dimension. Say it's not like for 2-dimension we are going to use p equal to 2.
So for same problem, if you use p equal to 3,
say p equal to 3, p equal to 4 is not having any kind of relationship with the dimension of the data.
Okay.
Have 3 observations like a 3 features like A, B, C, and this is observations. Observation 1, observation 2, observation 3, observation 4. So now A, comma, let me erase. It looks like a 1, then it will confuse you. So it is A, B, C. A, B, C are some input feature. Like say A is an age, B is an salary, C is a credit score, something like that. Right? So this is O1 is the observation 1, observation 2, observation 3, observation 4, observation 5. Say I have some numbers here. 2, 4, 3, 1, 3, 1, 0, 2, 5, 1, 6, 3. Right? So if I want to compute the distance between O1 and O2, how can I compute?
2 minus 1 also plus 4 minus 3 also to 3 minus.
Yeah. So it is like if it is Euclidean distance. So if I ask you what is the dimension of this data set, what is your answer?
3 dimension.
3 dimension it is.
It's a 3 dimension as 3 feature, but it is not that as it is 3 dimension we are going to use the p value as 3. Right? So that is power value as 3. So if you want Euclidean distance, only the power you will be using as only as 2, because the distance we are computing, the difference we are computing by comparing one feature of one observation with the other observation. So here this A I'm just comparing with the A value of the next observation. Then this B value of observation 1 I'm just comparing with the B value of the observation 2. Similarly, the C value of observation 1 I'm just comparing with the C value of observation 2. So basically that equation is like 2 minus 1 the whole square plus 4 minus 3 the whole square plus 3 minus 1 the whole square and if it is an equivalent distance. If you want this for p equal to 3, if you want to compute this for p equal to 3, all the so with respect to that Minkowski, so all the powers here you have to put it as 3 and all those things rather than taking square.
So what is the meaning of 3 here? That's my question.
No, as I told, this is an hyperparameter. No, so we are actually modeling that distances. Generally for p, we won't give power as in terms of odd value. Generally, we will be giving the even root only, because if I give the odd root, then obviously there is some kind of j kind of stuffs will happen. So it could be
so 4. If I give 4.
If it is give 4, you are actually amplifying your distance in a different way. But once you amplified, once you say if you take 4 and once again here if you take this rather than taking the root with respect to 2, if you are taking the root with respect to 4, then that 4 effect, that power 4 effect, once again you are bringing into a normal scale, right?
Yeah.
So that overall that essence will remain same, right? But still that some kind of internal relation could have been exist that we can't mathematically capture. That is the reason why it has been given as hyperparameter. But if you see, if you are squaring something and if you take square root, then you are bringing that to the normal number. Similarly, if you are taking the power 4 and once again you are taking the square root with respect to power 4, then obviously again you are bringing that to a normal scale, right?
Yes, the value will be decreased in that case. If it is power 4, the value will be still it will decrease, right? 1/4.
But after taking that power 4 and taking 1/4, will 4 and 4 will get cancelled out and that essence will remain same, no? Yes or no?
Because anyway, value will be decreased. Yeah.
See, this and this, what is the difference?
Both are same in this case.
Yeah, so that is the exact thing here also it is happening, no? But it is because of the difference that the value will actually change. So whether it is having any impact or not, that we have to build and see. But power 2, power 4, power 6, power 8 with respect to one single number, if you see that essence is actually same. Are you getting that point?
Yeah, sir, but in case of odd numbers, it will give you the complex number, right?
Yes, yes. So generally we can't, but I don't know as really whether it is giving the complex number, because even if it is negative here, once again we are taking that cube only, no? So here if it is odd, then that power root is also odd, then that I into I, that kind of stuff will make that to kind of
it will be odd only. It will be I only.
It will be I only, even after taking the of course,
if it is square, then it's fine. If it is not a square, then
say square root of any negative number is actually I, will give I, but odd root of any negative number will really give I.
Even because it's I square into I, so I square is -1 and I is already a complex number. So if it is a power,
no. My thing is root of -1 is I.
Yeah.
Right. Say if it is this one, whether this is I.
I think it should be
I power 1/3.
-1 whole power 1/3.
Sorry, minus
1/3.
Minus 1/3. But whether we can call this as I, whether it's a complex number, I'm not sure about it. Right? Anyway.
Yes, sir. Here we can take -1 root -1 outside and then -1 2, right?
Yeah.
You can write it as I power 2/3 and I is nothing.
Actually, it's a minus plus minus I.
So it is -1 right at the end. Anyway, we don't need to just go into that. So our package will take care of that. Anyway, we are going to use that P as some kind of hyperparameter if you want to see your model performance for the IRP. But anyway, basically, if you see, if you are squaring it and taking the square root, if you are taking the power 4 of it and you are taking 1/4 root, then that essence will basically remain same. So in terms of performance, you can't see kind of drastic changes like for taking the P equal to 2, it is giving something, and P equal to by taking P equal to 4, so the drastic your model won't drastically change its performance, because if you take any one number and square it and taking the square root will bring back that to a normal scale. Similarly, if you take a power 4 and take 1/4, once again will bring back to that same normal scale. So that impact of changing that P won't be actually much once you increase the value above 2. Right, but anyway, P equal to 1 and P equal to 2, there is some reasonable change because we are squaring it, and in another case we are not squaring it. That is what we have seen. So whenever you take P equal to 2, it's actually giving you the shortest distance, Whenever you give the p equal to 1, then it is giving you the maximum distance. So most of the time we will be using these two things, but of course p is available as an hyperparameter, so that we can tune and we can even explore for the higher value of p whether my model performance is really changing drastically or not. Right? So this is about the different distances. This is about the different distances through which I can find the difference between one observation and other observation. But how I am going to use these distances to make the classification result? How I am going to use those distances? Say whether I'm using Euclidean distance or any distance of power p, or I'm just using Manhattan distance, whatever. Basically, it's going to tell how one observation is actually deviated away from the other observation. That is what fundamentally I'm just going to get, right? So if I get that information of how one observation is deviated away from the other observation, or what is the distance between these two observations, how can I use this distance information to make the classification, in our data? So for that, let me show you one Excel sheet. Fine. So I have this simple sample data, right? So sensor 1, sensor 2. So there are 2 sensors installed in my plant. So based upon the sensor value, I'm just going to control the switch position. I'm going to control the switch position. Say if sensor 1 and sensor 2 are number like this, 2.34.1, I'm just going to on this switch. If it is 1.92.7, people made the switch position to off. So similarly, so this is the past data. So in past, for which value of sensor 1 and sensor 2, what is the corresponding switch position? That information is given in this data set. So now we are going to calculate, or we are going to see for this new data. For this new data, this is a test data. This is the already available data. So this is what the pattern that happened in that power plant. Whenever the sensor value is like this, and whenever the sensor 2 value is like this, these are the switch positions. Now, one new sensor data is coming. The new sensor data is 3.5, 3. Right? In sensor 1, the number that I'm getting from that sensor 1 is 3.5. From the sensor 2, I'm just getting the value of 3. Now, with respect to this data, what is the decision that I need to make? What is the decision that I need to make? So everyone have the ability to make this decision to naive Bayes, right? Yes or no? It's the same problem. If I ask with respect to the naive Bayes, you will just fit this data in one, fit this sensor 1 with respect to one distribution function, and you will fit the sensor 2 with its distribution function. And for 3.5, what is the probability? For 3, what is the probability? You will compute, and overall probability for on and off you will be compute. And if you put that in Bayes, you will get it into Bayes formula. You will get it the probability for on and probability for off. You can do that. Similarly, you can do that. Can you do this with the decision tree? If I ask you to do with the decision tree, at least you have an idea. So I have to find what is the sensor 1 Gini, and I have to find what is the sensor 2 Gini. So of course sensor 1 and sensor 2 are continuous number. So I have to calculate the moving average, and with respect to that moving average, for each and every moving average, I have to find the Gini, and which Gini value is less, that I have to use as a threshold for that particular sensor. So I have to split the data. So whether after splitting the data in the new node, whether the new node is pure or not. If it is not pure, once again I have to split that data. So like that you have to do the decision tree also. So similarly, how to do the KNN, that we are going to see with respect to this simple toy data. So now, as this is a test sample 3.5 and 3, I'm just going to find the distance between each and every sample in my data with respect to this test sample. With respect to the test sample, here you can see D of S1, T1. What is the meaning of D of S1, T1?
Distance between S1 and T.
Distance between the T1 and S1. Can you people quickly do simple calculation and can you tell me whether the value that I have put it here is correct? How will you do this? 3.5 minus 2.3 the whole square plus 3 minus 4.2 the whole square, and you have to take the square root. So everyone agreeing this? If you do that computation, you will be getting 1.69. Just check it out. Even in your Jupyter notebook, you just simply type it and tell to me. 3.5 minus 2.3 the whole square, because this is sensor 1, this is sensor 1. So 2.3 minus 3.5 the whole square plus 4.2 minus.
Yes, we're getting the same.
You are getting this thing. So here in Excel itself, I have calculated this. So B2 minus 3.5 the whole square, C2 minus 3 the whole square, because this value is going to be remain constant, and this B2 is going to be changes B3 for the next row, B4 for the next row. So I have just calculated this, and we are getting 1.69, 1.62, 0.94, 1.7, 1.9, 1.9, 1.3, 1.8. So this is the distance between each and every sample in your data to the test sample. Anyone have any doubt in how I arrived with these numbers? Clear, right? Yes or no?
Yes, sir.
Yes, sir. Yes.
Right. So now the thing is, out of these different, after computing these distances, if I ask you which observation is close to my T1 out of this observation, out of this 8 observation from S1 to S8, if I ask you which observation is close to T1, what would be your answer?
S3.
S3. Why?
0.9 distance.
Minimum Euclid.
The distance is less. So because this is a dissimilarity measure. In terms of distance is a dissimilarity measure. As for dissimilarity measure, the value should be low so that I can call that as close data or neighbor data. So here, out of all other observation, out of all other distances, this particular distance is actually very less. So the distance between S3 and T1 is 0.94868. This is the least distance in this distance vector, in this distance array. So I can tell this is the neighbor. This is the nearest neighbor. S3 is the nearest neighbor for T1. If I'm making the statement like S3 is the nearest neighbor for T1, is everyone agreeing that?
Yes, sir.
Right. So now, what is the class information of that nearest neighbor?
On. Switch position is on.
Switch position is on. So that for that nearest neighbor S3, we know what is the switch position. The switch position is on. So what I'm doing is, for this particular test data, I'm making the classification result. I'm just making the decision about the switch position as on. So which means I'm just putting this data under the on class, because I saw the nearest neighbor. The nearest neighbor switch position or the nearest neighbor class value is on. So I'm just assigning that nearest neighbor class value for this particular test sample. So I'm just going to classify this 3.5, 3 input as on class. The switch position corresponding to this test observation is on. Everyone got this point? Yes or no?
Yes, sir.
Right, but making the decision with respect to only one neighbor is not actually preferable. It's lead to an overfit problem. If you just make your decision with respect to what your one neighbor is telling, obviously that leads to an overfit problem. You are actually you are not seeing in a general sense, right? So you are very specific to what your neighbor says. You are not seeing with an bird eye view. You are not seeing that in a general approach. How many of my neighbors are saying, how reasonable amount of my neighbors are saying. You are making your decision with respect to only one single neighbor, then obviously your model will overfit, right?
And if you take average, sir?
Yeah, I will come to it. I will come to it. Say here there is no need to take the average because that output column is actually discrete, right? So if you are using this KNN for a regression purpose, you will be taking the average. I will come to it because some half an hour I will spend maybe in our next class. how to use. We have discussed decision tree, and we have discussed this KNN, and also we are going to discuss random forest. So once I finish that, I will also speak on how we can use these three algorithms in regression point of view also. So even though this is a classification residency, we will be discussing like how we will be using these three algorithms. Concept wise, it is remain same. Only that in output side we have to do some kind of modification so that we can also use these three algorithms for doing regression tasks. So that math concept I'm just discussing for about half an hour in any one of our sessions. So now
to discuss XGBoost also.
That is, we will be discussing gradient boost in detail.
Okay.
XGBoost is an extreme gradient boost. XGBoost math we can't really tell, because XGBoost is an optimized version of your gradient boost. Gradient boost we will be discussing in detail. So that if you do some kind of optimization in terms of changing its working speed, calculation speed, and all those things, it's become XGBoost. So if you know the gradient boost, that is the kind of same math which is actually applied behind your XGBoost also. We will be discussing that in detail.
Sure.
Yeah. So here, if you see, I'm just rather than taking a decision with respect to one neighbor, now I'm just considering three neighbors. So this is my first neighbor. Let's highlight this. Then who is my second neighbor? Who is my second neighbor?
Yes, 7.
Yes, 7. Yeah, 1.3. So he is my second neighbor. Then who is my third neighbor?
S2.
S4.
S2.
S2. No? 1.62. So this is my third neighbor. Now, with respect to the one neighbor, what is the predicted result that we have made for this data? With respect to one neighbor, we have made the result as on, right?
Yes.
With respect to one neighbor, we have made the result as on. So what about with respect to three neighbors? Whether with respect to three neighbors, whether my decision is changing or remaining same?
Remaining same.
So S2 for this S2, what is the class output? What is the class output for S2?
Off. Off it is.
On or off?
Off.
Off, right? So you're not agreeing this? Say I'm just coming to know that these are all my three neighbors. So S2 is one neighbor. I'm just going and seeing what is the output of S2. S2 is off. What about S7?
On.
On. S7, that output is output class is on. Now I consider three neighbors. It's like I'm asking opinion from three of my friends, three of my close friends. Close friends are my close neighbors, right? So the two are giving one opinion and one is giving another opinion. So out of this three opinion, I will go by the opinion of the maximum people. So out of the three people, two people are telling that it should be in on position, and one observation only is telling that it should be in off position. So even with respect to three neighbors, my decision is, even with respect to the three neighbors, my decision is on. My decision is on. So is that the decision is changing if I go with 5 neighbors? If I go with the 5 neighbors, who is my next neighbor? S1, right?
Yeah.
Yeah.
So S1 is the next neighbor. And who is my fifth neighbor? S1 is the fourth neighbor.
S4.
S4 is the fifth neighbor. So now with respect to S1 and S4, S1 output is again on and S4 output is again on. So with respect to the 5 neighbors also, my decision is on. My decision is on. Right? So again, here the number of neighbors that I'm going to consider is an hyperparameter. Right? So I can't go with very low neighbors like k equal to 1, like asking only one person. Based upon that, I'm just making the decision. So that person, if that person is wrong, or that person may not represent the overall opinion, right? So obviously my model may overfit. For the new test data, if I take the decision with respect to that one neighbor decision, then obviously my decision may go wrong for the new test data. So obviously that is an indicator of the overfitting problem. So whenever k equal to very low, you may experience the overfit problem. What happens if k is very high? What happens if k is very high? What happens if your k is very high?
It's underfit.
So it will become underfit. You are asking so many decisions, right? So you are asking so many people. So obviously each and everyone will tell their opinion at the end, which opinion you have to take. There will be a confusion, right? Out of which your model can't really predict the output correctly during the training stage itself. So the bias error will become high, right? So if k is too much, your model will move towards the underfit. If k is very less, your model will move towards the overfit. So obviously it is an hyperparameter. So we will be applying our model for different value of k, and for which value of k my model is producing the good result in terms of bias error as well as the variance error. That I'm going to see. With respect to that, I'm just going to make my final model. So that is how you have to go with the choice of k, right? So now, say here with respect to this with respect to this three distances. Say for example, let me write it. Let me write it in a board. See, I'm getting the three distances: distance 1, distance 2, distance 3. This is the neighbor 1 distance, neighbor 2 distance, neighbor 3 distance. Neighbor 1 distance is say 0.3, and neighbor 2 distance is say 0.4. So it is 0.1, and say this is distance 1 is 0.1, distance 2 is 1.2, distance 3 is say 0.5. Say 0.5. So now say this actually telling that it belongs to on class. These two are telling that it belongs to off class. These two are telling that it belongs to off class. So obviously out of these three neighbors, all are three neighbors. Using these three neighbors, you are saying that two neighbors are telling that it belongs to off, and one neighbor is telling that it belongs to on. So you will be go with the majority decision. So the class label for your test data you are going to declare as off. But sometimes you can also see what is the weightage, with what confidence it is actually telling that it is belongs to this on class or off class. To what confidence? So we say how your what your closest neighbor is telling, and what is your nearest kind of farthest neighbor is telling with respect to these three neighbors.
Closest is saying on.
Closest is saying on. Whereas these two fellows are telling off, but these two fellows are quite actually distanced away from me. Quite actually distanced away from me. So sometimes people will compute like 1 divided by 0.1. So this measure they will calculate as 1 divided by 0.1. What is 1 divided by 0.1? 10, right?
Yes, sir.
Right. Similarly, 1 divided by 1.2 and 1 divided by 0.5. So what is 1 divided by 1.2?
10 by 12.
How much?
10 by 12, 5 by 6.
In terms of fraction?
0.3.
And 1 divided by 0.1.
5 by 6.
Right. So if you see two things.
It's not 0.3, sir.
Sorry? Is it correct, right? These two numbers?
No, sir.
This is 0.875.
0.8.
Okay.
0.8.
So if you add these two numbers, you will be getting something around 2.875, right? Yes or no? Yes or no?
Yes, sir.
Yes, 2.83. Yes.
2.83. Okay, 83. Whatever. So let me calculate. 1 divided by 1.2 is 0.833. Fine. So 2.833. Fine. So which means even though people will calibrate this as a kind of weight. So this is weight and this is also the weight. So this is the weight of the neighbors, which is actually telling that it belongs to the off. This is the weight of the neighbor, which is actually telling that it belongs to the on. So even though in terms of on, the only one observation is telling like it should be there in on. Only one neighbor is telling that it should be there at on position. The weight of that is more. The weight of that is more. Whereas the other two observations are telling like it can be off. The position should be off, but the weight of that two are not actually very high. The weight, if you see, it is 2.83, which means these two neighbors, even though I'm just considering these two as a neighbors with respect to the whole data, but it is not as close as this D1 or not as close as this first observation. The first observation is very close and he is telling some decision, and that observation is telling some decision, and the other two observations are not very close. They are a little bit away from my test, but still they are my next two nearest neighbors. But these two nearest neighbors, even they are actually, even though a little bit away from me, they are the neighbors, because all other observations are much far. But their opinion is on the other side. They are saying that the switch position should be off. So sometimes we will be also taking the decision with respect to the weight, not just by seeing only the count, right? So there is two options to consolidate the neighbors result. One is just see the count information, how many are telling that it should be class 1 and how many are telling that it should be under class 2. So based upon that you can take a decision. The other strategy is what is the weightage, with what weightage actually they are telling that decision. So say sometimes there are 5 neighbors, 3 neighbors are telling that it should be off, 2 neighbors are telling that it should be on, but that sum of 2 neighbors weightage is actually more than the sum of this 3 neighbors weightage. Even though 3 neighbors weightage, 3 neighbors are saying that as off, I will go with an on option, because that weightage of the 2 neighbors who are saying it should be on is actually high compared to that 3 neighbors weightage. So this is how I can make the decision, or I can consolidate the results of my neighbors. I can consolidate my results of consolidate the results of my neighbors only by seeing that majority count, or I can consolidate the results of the neighbors by seeing their weight, or by seeing their confidence, at what confidence they are telling that, with what weightage that they are telling that. So in sklearn we can play with it. We can make the decision in a max vote way, or we can take the decision in a weighted way. So both the way we can build our model, for which kind of approach my model is giving me the good result, that I will keep as my final model. Got the point?
So here it will be on, right?
Here, if you go by the weighted approach, then it should be on.
So sir, how to decide? I mean, we should go with weighted or count one?
Yeah, that's why I told. So whenever I'm telling something as hyperparameter, there is no clear way so that we can make a comment like you have to go with this, you have to go with this. Whenever there is a confusion over it, which method to use or which kind of strategy to apply, say we can't able to mathematically relate that, then only people will give that as an hyperparameter. As I told, this is an hyperparameter. So we are going to explore our model. We are going to build our model with both these approaches, and we will be seeing the performance result in terms of precision, recall, F1 score, and for which approach you are getting the better result, that you have to use as a final approach, whether it's a weighted or non-weighted.
So for every problem, we need to find both the thing count and weighted. And based on that, we need to decide, right?
Yes. So in hyperparameter, yesterday we have tuned some max depth, minimum sample lift, something like that, right? So like that, there is one hyperparameter is there for this. So when you do the grid search CV itself, you can give both the option, and your best parent will tell that for this given data, which approach is actually giving you the good result.
Okay.
Right. So this is an hyperparameter. So even yesterday, Gini, entropy, two methods we have discussed. Which method I have to apply? Whether Gini method will give me the best result or entropy method will give me the best result. There is no direct relation to comment about it. We have to build the model with Gini, and also we have to build the model with entropy. And we have to see the result, and by comparing that result, we have to make a decision whether I have to go with a Gini based model or entropy based model. Similarly here too. So that is the reason why all those parameters are given as an hyperparameter in your sklearn. So any doubt? Say here, if tie happened, then weighted approach could be the better option, right? So if tie happened, you can use the weighted approach method so that tie condition can be easily handled by this weighted approach, right? Everyone agreeing that? Yes or no?
Yes, sir. Yeah.
Yes, sir.
Yeah, and also the thing is, whenever you are handling the classification problem with only two level, classification problem with only two level, or classification problem with any even levels, classification problem with any even level. Say whenever you are predicting 2 levels in the output, or 4 levels in the output, or 6 levels in the output, then obviously you have to go with the odd choice for the k. You have to pick your k value as something odd number, right? On the other hand, whenever you are actually doing some classification problem in which the output in the output column, the number of classes are odd. The number of classes are odd, like 1, 3, 5, something like that. 1 can't be there. So 3, 5, 7, like that. The number of levels in the output column, like cancer, stage 1 cancer, stage 2 cancer, stage 3 cancer. So there are 3 levels. So whenever that in output level, in output column, there are levels, which is in terms of odd number, then you have to go with the even choice for k. So you have to choose the k value in terms of even number. Whenever in your output column, the number of levels are even, then you have to go for the odd choice of k. So that is the one strategy that you can follow so that you can avoid ties, right? So ties definitely won't happen. But still, if it has happened, then you can use that is if you are not actually taken the k value based upon the approach that I have told, then definitely tie may happen. So if tie happens, in the sense you have to go with two approaches. One is weighted approach, or if you are not given weighted approach, you are still going with the maximum approach only. Then what happened in the sense sklearn automatically go and see what is the class distribution, in which level is actually occurred lot in that particular data set. Then that level has been assigned for your observation. So like that, the sklearn will handle the tie cases, right? So this is the math part of it. So nothing more with respect to the mathematical part. You need to know what are the different distances, and you need to know how can I choose the neighbors, right? So that is the that is the way that these are the only two things that you need to know about the K means that is K nearest neighbor. What are the different measures that I have to use? What are the different measures which are available? And what are all the different ways through which I can identify the K? What is the impact of K that will replicate on our model? What is the problem if I choose K value as very less? And what is the problem if I choose the K value as very high? So very high K value lead to the underfitting problem, and very low value of K will lead to the overfitting problem. How to decide how many neighbors we need to consider? See, Harinath, what do you think? After discussing this K neighbors, if I ask you the hyperparameter for K neighbors, can you list few parameters without seeing this sklearn package? Can you tell what are all the hyperparameters for K nearest neighbor for KNN?
K is the hyperparameter.
So K is the hyperparameter, right? Because
and
for
distance
K equal to 1, my model may behave some produce some output. When K equal to 2, my model will produce some output. For K equal to 3, my model will produce some output. I can't really tell for which value of K my model is produce very high output, or for which value of K my model will produce very low output initially itself. So I have to build the model, and I have to explore my model for different value of K. Then after that, I can even plot K versus bias error and K versus variance error. I can plot it, and if I'm getting some graph like this, then I can choose this point. Because in terms of variance error and bias error, this K value is giving me some kind of less number. So I can use this K as my final model. Final model's K value. Got the point, Harinath? Right. So that is the reason why we are calling K as an hyperparameter. We have to build the model for all the possible value of K. Then we have to make the decision. Then what could be the other hyperparameter? What could be the other hyperparameter for KNN? P. Because through P we are controlling the distance measure.
And type of distance method.
Yeah, what type of distance? For each and every distance, your model will produce different results. So how each and every distance is actually impacting your model, that we can control. Then what is the third one? What would be the other hyperparameter?
Distance type.
A distance type has been again, of course, in sklearn it is
Yes,
there.
same it is.
Type you can control with this itself, no. Then, with respect to the concepts that we have discussed,
the weight.
Prediction
is
Euclidean or
while we take the opinion, what kind of opinion? I computed the nearest neighbor. I also saw the nearest neighbor's output. With respect to the nearest neighbor output, in what way I'm just going to take the decision? Whether it is kind of vote-based decision, or it is an
weighted
decision. So that I can control. So which means for vote-based decision, what is the result? For weight-based decision, what is the result? I can see, and the best one I can pick. Right. So these three are actually an hyperparameter. Can you quickly go to Google and see what are all the kind of arguments they are giving for us to control the sklearn dot K neighbor classifier. See, this is the weights. This is what I told. No, whether it's a distance based, it is going to whether it's going to give the importance to the distance. Based on the distance weight, it's going to assign the final class, or it is uniform. Uniform means all the neighborhoods are given to the same weight. That is irrespective of whatever the distance of my neighbors, what my neighbors is telling, whether the neighbor is telling it belongs to class 1 or class 2. That is the only thing that I need to see. So by passing some information like uniform or distance, I can make the decision in a weighted way or in a non-weighted way. Non-weighted way only, it's an uniform way, and also n neighbors. And this one is another hyperparameter is algorithm. This algorithm is like optimization. We can't really speak for it. If you want, you can go through this algorithm by yourself. It is like in KNN, we are actually doing lot of computation, right? I have to take one test sample, then I have to compare that test sample with all other sample in my data set. So it's a kind of huge computation. So how effectively we can do in an optimized way, how effectively we can do so that we can save time, we can save resources. So in that way, there are different strategies, auto, ball tree, KD tree, brute, and all those things. So, but anyway, that is that we can't really speak with respect to that KNN classification application. This is generally how internally that yeah, smartly, it is like a kind of shortcut. You can rather than deriving the problem in a proper way, you can quickly apply some kind of shortcuts so that you can derive it in a quick way, right? So in that sense, this algorithm, different algorithm will actually help you to improve the performance of the model. But applying those algorithms won't actually reflect in terms of accuracy, in terms of F1 score, in terms of computational ability, in terms of computational optimization. These different algorithms will help you. Again, this leaf size is actually a kind of parameter which is actually controlling this type of algorithm. This is nothing to do with whatever the discussion that we had with respect to KNN. And also, if you see P, its P is actually by default it is equal to 2, and by default the metric is also a Minkowski, which means Minkowski with 2 is what distance?
Euclidean.
So Euclidean distance. So by default it will calculate with respect to the Euclidean distance. If you want, you can actually play with it. And also, why they have given metric as one separate hyperparameter is, so Minkowski is the kind of standard equation. With respect to the standard equation, if you control the p value, you can achieve different distances. Apart from that, say you are coming up with your own distance measure. You are writing your own algorithm, and you are coming up with your own distance measures. In the sense, you can apply your own distance measure in this formula, in this KNN package. So you can externally write some kind of function. That function you can pass here as a metric, so that now KNN will compute, will do it all its process by using your equation as a distance equation, your equation as a similarity equation. So that possibility is there. That is the reason why they have given this as one separate parameter. So like that, you are there. So n job is one parameter which actually control the hardware. If n job, if you give us -1, if you give n jobs as -1, then it will actually use all your system resources effectively. Say if you have multi-cores, in your system, all the cores it will actually use, all the hardware it will actually utilize to do its computation. So in that way, you can actually modify the you can actually get the best performance out of your model. Of course, this n jobs, those algorithm, that leaf size, everything is related to the performance, not related to the performance. It is actually related to the time, power, memory, that efficiency in terms of time, power, in terms of yeah, the memory. So how effectively you can implement the algorithm. So in terms of accuracy, in terms of F1 score, in terms of recall, if you want to control your model, you have to control with that distance metric, P, and what is the kind of weightage that you need to use, and what is the K neighbors that you want to apply on your model. So these are all the things you need to control so that you can control the performance of the model. Right. So this is about the hyperparameter. So next class, quickly I will just walk you through that code of the K neighbors, because code of the K neighbors is very simple and straightforward. With respect to sklearn, in the same way only we are going to apply that function. But another concept that I want to discuss with respect to this KNN is, so I have demonstrated the working principle of KNN using this data. Do you think that whether my model is doing anything during the training stage? Generally, if you see linear regression, your linear regression, in training stage or linear regression or logistic regression, in your training stage, this equation has been computed. Y equal to b1 x1 plus b2 x2 plus b0. This coefficients b1, b2, b0, everything will be computed during the training stage. Yes or no?
Yes, sir.
Right. So once I give the x test input, this x test will be get applied into x1, x2. Right. Then for the new incoming input, the same coefficient will get same trained coefficient will get multiplied on this x1 and on this x2, and it will produce the output. It will produce the output for this x test. It will predict the output for this x test. Similarly, if you take your decision tree, for that whole train data, decision tree will make the structure. Decision tree will make this structure, right? Once your new test data comes, with respect to this test data, the test data flow in any one path, and it make the decision as, okay, it is class 0 or class 1, right? So this tree structure has been formed with respect to the train data only, right? So similarly, in your KNN, in your k-nearest neighbor algorithm, your model is creating anything, or your model is constructing anything during your training stage?
No.
During your training
Distance.
stage?
No.
It's taking the distance. Right?
Say distance, when it is actually taking the distance? These distances we have computed after we have received this test sample, right?
Yeah.
Yes.
Before I receive test sample, is there any way that I can compute the distance? No way, right? Because there's a distance between my test sample and my each and every observation. So in KNN, there is nothing called really nothing called as training. Of course, training with respect to sklearn, we have to give, because that the structure is ready, kind of with which distance I need to calculate all those things. So your model will actually will be defined with what is the p-value, what is the metric, what is the weight, whether it's a uniform or distance, and all those things will be assigned to your model. But your model really don't do any kind of computation during the training stage, right? So mathematics, yeah.
Sir, in this case, how do we get the bias error and variance error?
How do we get
bias errors? Because there is nothing is happening in test training set, right? So there will not be any performance, I mean accuracy and other things in the training.
No. See, the thing is, as far bias error and variance error, see, this S1 data is there, no? This S1, say whatever this 8 data are there, no? In this 8 data, this S1 itself is used for training. This S1 itself is used as T1, and with respect to that, it is used to compute what is the class. And S2 is used as T2. With respect to that, it will use to compute what is class. And this S3 itself once used as a T3, and with respect to that, it is used to find what is your class. In that way, it is used to compute the bias error. And for any new data, for that any other 30% of data that that you already splitted for testing, that has been separately applied on this, and it will the kind of error it is making, that you can model as some kind of variance error, right? But anyway, there is no real point in that. But anyway, you are in your sklearn, while you are applying it, it will use to give the bias error and variance error in this way that I have talked about now. What the point?
I think, sir, here actually we are doing hyperparameter tuning, so it's memorizing the hyperparameter. And based on that, actually, we are doing, bias and variance error. So if the number of neighbors are more, so in that case, your, that variance error will be, more. And
that is true. That is true. What this question is, say there is say here there is nothing called that fixed train model. There is nothing called fixed train model or trained structure. Then how we are actually we used to call it as your bias error is nothing but the error made during the training stage, right? So I told like in KNN nothing called train model. So only once you get the test input, then only that model will become active. Then with respect to the test input only, it actually compute all those distances and it is computing your performance. So in that case, how can I compute the bias error? How my sklearn is computing the bias error and variance error in the sense, say you have an 100 data and you are splitting that 100 data into 70 and 30. So with that 70 data, only that say whenever there is an 30, let me write that. Say you have 70 data, this is for training, and you have 30 data, this is for testing. Now this 30 data one by one you are comparing with this 70 data and you are making one result, no? That is actually your test result.
Yeah.
Now the 70 data itself, in the 70 data, I will take one data and I will actually compare that one data with this 70 data again, and I will make some kind of result. No, that is nothing but my train result. Got the point?
I think here no parameter, only hyperparameter is there. So model not learning anything, it's memorizing.
Yes. Yes. So there is no parameter. So that's what I'm telling. Like, so it is the only computation it is actually doing is distance. That distance it is actually computing in a real time. Only after the test sample is available, it is actually computing it. But still, if you apply by using cross-val score or by splitting the train and test, if you apply it, actually you can compute the bias error and variance error. But that bias error and variance error is actually computing in this way. That 70 data that I have used for training, that 70, with respect to that 70 data, each and every data has been once used as a test, and with respect to that, it will compute the error. That is nothing but your bias error. Now, that's with that 70 training data, that remaining 30 data will be get compared, and with respect to that error, it will compute. No, that error we will be calling as an test error. Then the difference between the train error and test error is more. Then we are calling that as a kind of high variance model. So in that way, only the sklearn will compute it. But obviously there is no training stage model. Your model is become only active. Your model will doing its computation only it receives some test input to it. So it is not actually using your data and developing some model, and then it is actually using that model on the test data. Only after test data comes, it actually do all its mathematics. Before you feed the test data, your KNN won't do anything. It just wait until it's received the test data. That is the reason why your KNN is known as lazy learner. This is the reason why your KNN is known as lazy learner, because it won't learn anything ahead. It won't prepare for your exam before. Just it will go and face the test in an real time. Got the point?
Yes.
Any other doubt with that? So next class we will do the programming part of this KNN. Today I thought of doing it. But anyway, next session we will be doing this programming part with respect to this multi-class before going into the random forest. So if you have any doubt now with respect to the KNN or Navier that we discussed today, you can ask me. Yeah. Yes, Rina, you can give a poll. I think the KNN question that they can answer, because all those concepts I have covered.
Yes, sir, I have launched it.
Okay.
So the 3 questions I launched it on
Sure.
naive Bayes and yeah.
Yeah. Linus, shall we discuss the result?
Sure, sir. Shall I end the polling, sir?
Yeah, of course.
Shared the results, sir. Students have given the third option. 85% students have answered for the first point. That is in 2 as the option. For the second question, okay, second question we have got 47% answering the first option, and 15% answering the second, 32% answering the third, and 6% answering the fourth option. And for the naive bias, 68% have answered the second option, C and D.
So let me start with naive bias. So which of the following statement about naive bias are true? The first statement is naive bias calculate the probability of one class only to make a decision. So whether that is true or false?
That is false.
False it is.
So it need to take the thing for both the classes. So naive bias can't handle more than 2 classes.
It can handle it multi-class.
So it can handle it because the same way, whatever the, so if it is only 2 class, then we will group our whole data into 2 groups. Then we will apply 2 bias rules. So if it is 3, then we will group our data into 3 groups, and this likelihood we will be calculating for each group. So it can handle very easily the multi-class.
Yes.
Naive Bayes assumes that the input features are independent of each other. So that
True.
is assuming. But keep the point in keep one point in your mind. It is assuming, but it is not that we need to really make our data to be perfectly independent. So that is the reason why it is known as naive Bayes. So naively it is actually doing that by assuming like that. Then the last point is naive Bayes assume that the continuous variable are normally distributed. So
That is also true.
True.
that is also true. So option is
C and D.
B, C, D.
yeah.
C and D.
BCT, right?
Sir, CD. B is wrong.
B also true. Can't handle more than 2 classes. So it
Yeah,
will
yeah.
handle.
It can handle, right?
It
Then
can handle. It can handle.
Yeah,
Yeah,
it
it
can
can
handle.
handle.
So it's
Oh,
false
it's
then.
yours.
B.
It's false. Yeah.
C and D, right?
So it is C and D.
C and D.
Then that P defaulter that we have discussed morning. The next question is, say our model is built on 3 features: size, price, season. The 2 observations are given as 2, 1.5 summer, and Y is 1, 0.5, winter. Consider the season have only 2 different levels. Find the Euclidean and Manhattan distances.
Taken summarize 0 and 1.
Sorry?
Summarize 0 and winterize 1. We can take like that and we can.
Yes. Yes. You have to do any one level for winter. That is any one level you can assign as 1, and another level you can assign for 0 as for summer and winter, and you can do the calculation. So by seeing that Manhattan calculation quickly, I can tell Manhattan is just a difference,
3.
right? So 1, 1, 1. So it's going to be 3. So first or third? Which one?
Third
one.
Because the same 3 only you will be getting in terms of Euclidean only, because the difference is actually 1. If you square 1, the value is going to be remain same. So it is actually √3. So it is 1.732. So that is the third answer. Then for which value of P, Minkowski distance is equal to the Euclidean distance? I think every one of you might answer that correctly. So what is that? P equal to 2. Right? So this is what the answer for this particular quiz. And morning, actually, while I'm starting this session, Satya asked me to doubt about the kappa. But anyway, kappa statistics we will discuss in our next session. But anyway, I think you have one in class.
Question. One
right?
question, sir.
Sorry?
Yeah, only one question we do have.
So I will give you the syntax, because the concept I have to explain in a proper way. Otherwise, there won't be any point in it. You can see my screen, right?
Yes, sir.
Yes.
So as for implementing that, this is very simple. So from SQL and metric, we have Cohen-Kappa score. Using that Cohen-Kappa score, we can similar as we used to apply accuracy, as we use accuracy score or F1 score or precision. You can simply use this Kappa score metric also. The input is your Y test and Y pred. You have Y test and you might compute Y pred from your model. If you just apply these 2 numbers in your Cohen Kappa, you will get that value. So what that value, how to calculate those value, what is the real inference, all those things we will discuss in our next session. It is like even though it's a poor without building the model, what is the kind of expected accuracy? Even though I have built even though I have not built the model, just by random guess, what is the kind of accuracy that I can get, and how much accuracy my model is getting? The difference between that 2 things is actually a kappa score, right? So whether my model is doing the job, or it is just by luck, or by my model is really doing anything to predict this stuff, or just like that, even though if I am not deploy my model, this kind of accuracy I can expect from this data. So in order to measure these 2 parameters only, we need something called kappa score, whether my model is really actually producing this output, or it is just like that, that output is actually happening. So what is that expected accuracy and what is an observed accuracy? So what is the difference between these 2? That we can model through the kappa score. So next session, I'll be discussing this. So as of now, for your in-class, you can use that simple score, and you can find that kappa score and finish your in-class. So don't keep that as pending. You can finish that. We'll be discussing this concept of kappa score in our coming session.
Sir, is there any parameter for threshold for this? Because I got this one. I updated it as well. I got 0.08. But the question says consider threshold value as 0.18.
For kappa score.
for kappa score. So that's where I'm not very sure.
Here we have YPRED, right? So for calculating Y prediction,
maybe
we
they
have to
might
take the threshold as 0.3.
Let me see that. Let me see the kappa score. As per this Cohen kappa score, it's not allowing any threshold to give. But you can compute. Say they may ask that because we have discussed, how to tune our model with respect to different thresholds. So in that sense, they might have asked you. So they may ask you to produce the YPRED with respect to the threshold. Then you have to use that YPRED that you are getting with respect to the threshold of 0.18 here, and you have to calculate the kappa score. That they might have asked.
Got it. Sure.
Yeah. Fine. Any other doubt? I'm getting some question. Yeah, we have already addressed that. Fine. Any other question, guys?
Next class.
Sorry?
We'll ask in the next class. Presently, we don't have it.
Sure. Go through it. And also, I have actually shared the KNN coding part also. You just go through it, right? Next class, I will just take you into that code part in detail. But rather than typing it, we can just walk through that KNN code part, because the same thing only we have to do, right? So only that multi-class part I will be doing line by line, and I will be do some kind of calculation also, how to form the multi-class confusion matrix. From that, for multi-class, how to find the precision, recall, and all those things, and how to draw the ROC curve for multi-class. So that section I will do. The other section you can just refer in that Jupyter notebook that I have shared for KNN. Simply how to just call the KNN function, applying our data and getting the output. That is actually same as that of other machine learning algorithm. The extra part in that data set is actually I have used some multi-class data set. So I will be discussing about that particular data set. That data that I actually derived from some image, some crop image. From that crop, I will be sharing that also. What is the kind of strategy that I have used to extract some of the numbers from the images, so that I have constructed that as a structural data. So those things quickly I will be discussing in next session before jumping into the random forest. Fine. Fine, guys. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.